It sure has to work. It's actually pretty comfy.
I really wish we could like put the cameras up on one of the screens.
I know. Because the problem is Teams is not really designed to do mixed hybrid meetings.
I see.
Yeah, okay.
Well,
it's saying that I'm
that
recording.
these aren't separate displays.
Well, no, not even that, but like I can't do the presenter view like in Teams and have it.
Interesting.
Yeah, so I have this. This is what just so you can see. So it's 9:25.
I can. Do you want me to hop back in the meeting and look, see what it looks like?
Very technical. The video. Let's see.
That's cool. That's what it looks like.
Does this belong? I want to put here something, just so I can take some notes. Thanks,
Okay. I also just shared a link in the chat that has the presentation on it, so that way that you can follow along too, if it's hard to keep up with the slides. And do the same thing with ground support.
Matthew, do you want me to stay in the meeting so we can monitor?
Yeah.
Okay.
It looks so extra gentlemanly. It kind of looks like a rocket, honestly. It looks like a
And I've done the same with the ground support files, so hopefully you can see them both. And with that, it is 9:25, so I think we're gonna get started here. And so we have this on Teams and in person. So there's a few people who have joined us online as well. So if you hear them call out, just know that they're from the Teams chat. So I'm going to get started. So I am Matthew. I am the president here at Cal Poly Space Systems, and so I'm just going to give a brief presentation and introduce Adam, who is the propulsion lead, who has been heading up our liquid engine. So this is a project that we've been working on. It's kind of been one of those projects that CPSS has been trying to do for a while, and now we're finally getting to the point where we have a design review ready to go. So with that, I'm going to just kick it over to Adam, who has a lot more knowledge about this project than I do. You just might need to click over the slides.
Okay.
Beneficial for people on the call to introduce themselves.
Okay, yeah.
So
Yeah.
knows who they are.
How about, we just do the alumni here. First.
Yeah. Any guests in the meeting, I think it would be good to have you guys introduce yourselves so that everybody here in person knows who's talking to, asking questions and everything.
Well, Bjorn, you can if you want.
Okay, yeah. Hello, so my name is Bjorn Kniesner. I'm from University of Munich as a guest professor at the moment. And my topics there are space, aeronautical and space propulsion, and I have a rocket team there myself. And I'm interested in all the rocket activities you have. And sorry, I wanted to come in person, but I'm only by bike here, and it rains so much, so I thought it would be better to just stay at home.
Yeah, thank you for coming. Definitely stay home. It's a little wet. Oh, cool.
All right, Miles, you're up.
Thanks for the introduction, Chris. Hey, I'm Miles, old CPSS alum, an old man, mostly work in manufacturing now. But I like commenting on the designs you guys make because it's fun and it makes me feel dumb. So yeah.
My name is Chris Larkin. I was the propulsion lead and vice president for CPSS in 2018 to 2019, I think. Oh God, I'm old. Yeah, also here to roast your guys' design and try and get towards something that won't blow up.
Awesome. Alec, we're introducing ourselves if you didn't know. I know you just got here.
Yeah, sorry. Hey, I'm Alec. I was the prop lead the year before Chris and was in the club, I think, for technically 6 years. And now in satellite propulsion development. Here to help tear it apart.
Yeah, thank you all for coming. All right, with that, we'll just get into it. So yeah, my name's Adam Hay. This is the work of the whole prop team. They'll come up here and introduce themselves later, but we'll just... All right. So here's just our schedule. We're going to go through some high-level design. Then we're going to get into the combustion chamber, the injector, the interface between the two, then some high-level manufacturing methods, and feed system design. And up there you can see just some pictures of what we have so far. All right, so high-level design, we decided to do an ethanol and nitrous mixture, 90% ethanol, and we're able to dope that down if we have any more thermal problems. Mixture ratio of 1.5, thrust of 25 pounds, a chamber pressure of about 10 bar, no cooling method this time, and pressure fed system. And the goal is to be able to integrate with the test stand and to scale this project up. A lot of these constraints are from either the department or just from like very like conservative metrics that we've developed. And so the goal is to, you know, make it bigger as and flight ready as time progresses. So a lot of these are very like light goals. The system.
So just to be on the same page, not a flight engine yet.
No, definitely, yeah, not a flight engine. All right. This is getting a little bit more into the combustion chamber design. So we first use CEA to calculate some things like gamma, the combustion temperature, and the molar mass, and those are shown here. And then we used RPA to size the combustion chamber. We went through our own calcs to make sure that everything checked out, and it did match RPA's calculations. And we'll get more into like the specifics of the nozzle and the combustion chamber in the next few slides. But this is kind of our process that we went through. And we designed the nozzle for ideal expansion at sea level.
Question there. So is the idea that this remains always just like a test cell unit that you can scale up, or would you eventually want to fly something like this?
I don't think we would want to fly like the heat sink. Yeah. At this point, no. All right, and then this is just on the nozzle design. So there's some equations there, some rocket equations that we used to get some of these parameters here, like the exit velocity, the coefficient of thrust, and specific impulse. Not the best specific impulse, but again, we're not going for like perfect efficiency here. We're just going for something that we can make sure it doesn't get too hot. Yeah.
Wait, I'm confused because your exit velocity and your ISP feel like tell two different stories. Like exit velocity being like out of the nozzle, right?
Yeah.
Like not your C star.
No, not the C star. Yeah.
Because your exhaust velocity should scale with ISP through G. But if I take 2124 and then divide by 9.81, I get 216 seconds.
Interesting.
Is the ISP from RPA?
I don't think so. I've got my code right here. There was a little bit of crossover between the RPA and the in my actual code, but I thought I ironed everything out. It might be.
Gotcha. I would double check that number. So yeah, whoever's taking notes, I'd take it as an action item to double check ISP because 109 seconds seems really low for a liquid. Like you can get like 70 seconds with cold gas thrusters.
Yeah.
So I would double check the ISP number because if you're getting 2124 meters per second exit velocity, you should be getting like 200 seconds of ISP.
Yeah. I'll double check it. Maybe it is more. Yeah, I'll look into it. It should be an easy fix, but cool.
Yeah, I mean, like that'll be pretty critical because that'll change your mass flow rate for a constant thrust as well.
Yeah. I think in my code I'm looking at right now, I must have pulled that ISP from RPA because I never went through ISP specifically. Oh wait, yeah, I did.
Copy. We can keep moving. Don't mean to derail, but that's definitely something to double check.
No worries. Cool. And this was the chamber sizing stuff. The RPA sizing outputs, we first were a little bit skeptical because the contraction ratio was so high. It was like 15 or 17 that it was first outputting. And that is like 3 or 4 times what I was expecting. But then going into Husel and Huang, it showed a couple of these graphs here that essentially like graphed experimental liquid propulsion systems. And these aren't the same pressures that we're experiencing, but if you kind of look at the graphs, it shows that our throat diameter, which is like around 0.37, contraction ratios are really high, or they have been for successful systems. So then we kind of went through the sizing again and like assumed that was okay. And then we chose the chamber length also based off of graphs like these that were in Husel and Huang.
Can you talk a little about what contraction ratio is and why that number was originally suspicious for you?
Yeah, well, I mean, so contraction ratio, for those who don't know, is the area of the combustion chamber to the area of the throat. And I don't know, I haven't sized something like this, but when we were going through the calcs, I was expecting something between like, I don't know, 3 to 5-ish, just based off things that I've heard of other people's engines. But then I think just because our throat diameter is so small and that it did make sense, that RPA wasn't outputting things that we weren't expecting, and that the calcs that I was doing also were consistent with what we were finding across other thrusters of this size.
How did you go about sizing chamber length? Was it like, it seemed like it was somewhat arbitrarily set at 2.5 inches, then you calculated L star based off of that?
Oh, no, chamber length, okay, so like there's a couple graphs in Husel and Huang. I think I have them in the appendix too, but the bottom right one, it was kind of arbitrary, like looking at those graphs and just sizing it based off of other people's thrusters that are that have these same metrics as well. I think a lot of the literature we were reading was saying that it's kind of hard to get a perfect chamber length or like a good estimate for it. So we wanted to go off what already has been successful and already exists.
If I can jump in here really quick, it'll be really difficult to get a good estimate about an L-star value without like a year's worth of work specifically on that, without any kind of physical testing. Do you guys have a slide on your injector coming up?
Yes, yeah, we have all that.
Yeah,
I'll wait for my comments on that until I see that one.
Okay.
Yeah. When we looked at this before, because like it should be, you have your contraction ratio, throat diameter, and chamber diameter, and then you like find an experimentally derived L star. Also, your L star should be 1.02 meters, right? Like it should have units. Or sorry, you're not in metric. Disregard.
I think it is. Yeah, you're good.
But like, yeah, it should be in. You should take L star that you know is like fairly decent, and then back out chamber length from that, right, Alec? So I was just trying to figure out if they like set chamber length. I guess they set chamber length based on some blocks and back out.
It was,
Yeah.
yeah. It's kind of a
If you're not
combination
gonna-
of both, if I'm being honest.
If you're not going to aim to do the chamber length determination experimentally or analytically, like I did, you're going to have to probably go with a standard L star value. Make sure your injector isn't too oversized, and then from there back out the rest of your chamber dimensions. But again, we'll wait and see what yours looks like. 1.02 doesn't seem too far off from expected, but if you underestimate, you end up with a flamethrower, not a rocket.
Yeah, and like that's like they're using. I feel like 1.5 to 2-ish is what I found was pretty decent for. There wasn't a ton of literature on nitrous and ethanol, but like 1.02 could also contribute to the low ISP if they're just like not combusting properly.
Yeah.
Double star as well.
I'll look back into some of my analysis on that really quick while we're going through this.
Cool. Yeah. It was a combination of both. Of like, because I thought an L star. I'm not 100% sure of like exactly what we should have been expecting, but when we got 1.02, it was like that seems consistent with what other people are getting. But we can look into that more, and you guys can comment more with what you see in the injector.
The only published value for L star for nitrous oxide ethanol is like 7.5 meters.
Yeah.
But that one's the worst. It's a backed out L star from the engine they were using, and just long enough, so they'd way overestimated.
Okay. Yeah. I think
is correct.
Okay. I think I heard you there. Dr. Niesner? Sorry, no.
Yeah. Sorry. I mean, we already talked about this. So for hydrocarbon fuels, I would recommend about 1.4 meters L star. But yeah, it depends on the injector. So as Mr. Bloom said, we should wait for the injector design.
Okay. Sounds good. Cool. Then we'll keep moving. And this is just a little bit about our material selection here. We've got a couple guys who did this trade, so they'll come up and talk about it a little.
My name is Matt, and
I'm Ethan.
So we're doing the material selection, and we narrowed our materials down to 3, which was aluminum 7075, copper 182, and stainless steel 321. So when selecting our materials to really consider, we were looking at the melting point, the cost per kilogram, thermal conductivity mainly, as well as the thermal expansion rate and the tensile strength.
Yeah, so we chose to go with copper due to the high thermal conductivity. Since our engine is going to be heat sink with a 3-second burn time, we won't reach thermal equilibrium. And so the high thermal conductivity will help to decentralize the thermal stress as much as possible.
Quick note, if you go back to the previous slide, units were in inches, whereas here everything's being listed metric.
Yeah.
Would be great if it was standardized across the project and the presentation. And then did you guys look into how much heat you're actually going to be dumping into the chamber? Like I see thermal conductivity, but do we know how much heat it can take before it becomes a problem?
Yeah, so I'll refer that question to Adam here.
Yeah, we did. Jake's about to get into that right now with the thickness of the material. So I think he's nice. So.
Are you guys going to touch on how much heat's being dumped in at the throat specifically if you're going to use a copper chamber?
Yeah, I don't think we go into the throat specifically right now. I think that's something that we need to look at for PDR or CDR. Yeah. But yeah.
Yeah, you'll probably melt the copper without any kind of cooling.
Okay. Hi everyone, I'm Jake. Where's the actual slides?
Does the arrow just work?
The one.
The arrow on the keyboard.
Yeah. Okay. Anyway, so in terms of analyzing the heat transfer, that was most of what we did for determining the wall thickness, because with our chamber pressure being as low as it is, our actual mechanical stresses that are in the chamber walls were far below the yield stress of the copper that we were looking at. And so ultimately, because we're doing the heat sink method, we needed to know how much heat we could transfer in without losing the structural integrity of our combustion chamber. And so in order to do that, it's kind of a complicated problem, but it was difficult to find heat transfer coefficients for the convection between the hot gases and the chamber walls. And since that's an overwhelming majority of how the heat is transferred into the walls, we had to figure that out. And so there was a method in the book by Huzel and Huang for estimating the convective heat transfer coefficient, which came out to be about 0.002 BTU per inch squared second degree Fahrenheit, which is a fun unit. Anyway, using that, I calculated like pretty much the worst case heat transfer across the entire thing, as if it were never really changing temperature and not dumping any heat, because our burn time is so low, and basically just did an estimate of how much copper volume we would need in order to withstand the heat, just on like a specific heat basis. Ultimately, this doesn't help us determine where like the hot spots and things like that are, and that would be really difficult to do. We need a little more time to do kind of more like a transient analysis on the heat transfer and actually look more at the throat specifically, because there's a good chance that this will melt. But ultimately, with the amount of copper that we have, with walls that are about 0.5 inches thick, we should be, I guess, more than fine hypothetically with the very worst case of our heat transfer.
Quick note, it looks like with the design, this is all going to be one piece of copper, is that correct?
That is
correct. Including the flange? So if this isn't a flight unit, there's not really a reason to reduce that thickness. If you want to play it safe, you probably just leave it super thick.
And then you also can machine it quicker as well, because you only have to do the inner mold line instead of outer mold line as well.
Right.
It won't look as pretty, so that is something to note.
Okay, awesome. Thank you.
I think Bjorn also had a note.
Oh, yes.
Yeah, so sorry, I didn't get the last two sentences of the comment, but so in general for the copper, I would not go beyond, let's say, 900 or 1000 K for the copper. You had a value of 1300 something, but yeah, I wouldn't exceed 900 or something for the copper. The heat transfer coefficient, there is a quite good relation, which is the Bart's relation you should maybe apply on this. And I'm not so familiar with this BTU per square inch units, but I would say you would have around 3,000 to 5,000 watt per square meter in Kelvin normally. In the throat, this will be the problem. So the chamber is probably no issue, the cylindrical part, because the heat transfer is quite low. But in the throat, you will have a quick heat up. So that will be the problem. And due to the high conductivity of copper, it could heat up quickly. So 3 seconds could be still long for this. So yeah, I would check it with this. So Bart's equation is quite good for this.
Okay. Yeah. +1 for using Bart's, but also I see you mentioning your thermal factor of safety here. Are you guys applying factor of safety for like an ultimate stress, or are you just using PR over T and then going based off that?
Okay, I guess that was probably not exactly the term I should have used for that. Really what I was saying is that we just had, essentially, based on the calculation that was done, we had about 15% more copper than was needed just to like have exactly the amount of heat absorbed that's transferred.
Yeah, but like, well, so going to the previous slide, I think, like you're sizing your wall thickness based on chamber pressure, some material strength, and then like, are you applying a factor of safety on that, or are you just assuming PR over T?
Oh, I mean, so based on the math we did, well, this is, it's kind of,
I use a factor safety too. When I was doing a lot of the stuff later in like the interface, which is really high, but
Yeah.
Yeah.
Okay, I'm sorry, did you hear that?
Yeah, it sounds like you're using factor of safety too. Is that factor of
Yeah,
safety?
Adam said he used factor of safety too for other stuff. The reason that I didn't include that on this is because the yield strength of the copper we were looking at was like so much higher than this was a very, very loose estimate on what the mechanical stress is. This was based on just like a thick wall. I think this was actually based on a thin wall cylinder, which like as a pressure vessel, which isn't perfect, but it gave us kind of like a ballpark estimate, and it's just so much lower than like the yield stress of copper is that didn't bother.
A quick note on this slide. You have the different strengths of things with respect to temperature and percentage of their initial strength, but I don't see the initial strength of the copper noted.
Oh, it's the brown line there. I didn't write it out. It was more for reference in terms of like what the relationship looks like.
I think they
what I was just trying to get at is that that there's no note for like or anything without experience.
Yeah, it was in the previous slide, but
oh, was it? I missed it then. That's on me. Sorry, disregard.
Anyways, yeah, just like want to highlight that you should be using a factor of safety on yield and ultimate, and then going from there. Like if your failure mode is not just like rupture of the pressure vessel, that's fine, and then you have to design to it being thicker because of other reasons. But like you should be applying factor of safety, and then keeping that consistent across everything that you're doing.
Okay, noted. Thank you.
I guess just to support what Alex said prior, it's just that if you're gonna treat this as a lab unit, increase your wall thickness. It doesn't hurt you any. That way you can at least get more fires out of it. You never have to worry about like, well, in the second fire, you gotta go and do all your, you gotta reassess what your current wall thickness is, what your actual is. It's just easier.
Gotcha. Okay. All right. Next we got injector design.
All right. How do you move the slide forward? I just want to know. It's just the arrow keys. Okay. All right. Well, hello. I'm Aiden. I've been the leader of the injector team, and yeah, the injector is the most complicated geometrical part of the rocket engine, and so we've been working on the design for a while, but there's a bunch of high-level design decisions that you need to make before you actually get into creating geometry. So we're going to go through those first. So the first thing that you need to decide is your mixture ratio. I know that was already indicated at the beginning of the presentation with the high-level parameters, but the mixture ratio, I guess I should have defined it, is the mass flow, the ratio of the mass flow rate of the oxidizer to the mass flow rate of fuel. And for our engine, we're using a mixture ratio of 1.5. Now, the reason we picked that it relates to our use of the softwares RPA and NASA CEA. We're going off of, I think, CEA for the mixture ratio and for the combustion temperature. So essentially, I created a curve of mixture ratio versus, ISP versus mixture ratio. And that should also been in the presentation, and it is no longer. But I determined that an optimal mixture ratio would be between 3 and 4, given our thrust and pressure, chamber pressure. However, optimal ISP is not necessarily all you want, because our method is our engine is uncooled, which means at the optimal ISP, it will have a very high flame temperature. And so you would like to decrease that flame temperature so that you have more room to work with and you don't have to make the copper so thick. So in doing so, we decreased our mixture ratio from between 3 and 4. So it would also decrease the it would also decrease the flame temperature, and we selected 1.5 as a mixture ratio going forward. Sorry?
It'd be great to have the plot of like chamber temperature versus mixture ratio. How much did it decrease your adiabatic flame temp going from?
I believe it was about 2800 Kelvin at the max and about 2240 at 1.5. That's what we are going off of.
Copy.
I guess it's between 4 and 5, not 3 and 4.
This might have been different. It's fine. It's fine. For reference, I'll just give it to you.
For reference. Sorry. Okay, I'll move on. Okay, so the big decision that you have to go through regarding injector design is the element type. So there are a lot of different ways to design an injector, and I mean like a lot of different ways. And that main decision of injector type governs everything else. And the most common type of injector and the most well documented is the impinging jet injector, where basically you have channels through which your oxidizer and fuel will flow, and they will exit the injector faceplate and they will hit each other. The two streams will hit each other at an angle, and this will create atomization, and it will be best for combustion. So you'll be able to ignite easier. So this is like a tried and true design and has been a thing since like the very beginning of rocket engine design. And so initial estimations of the injector orifice area, which we'll go into later, they indicated that with our hole size, we only needed one element, and that element would then be placed in the center of the injector faceplate. So when thinking about different ways to, different element types that we would use, there are several impinging jet types. You have unlike doublet, where you take one fuel stream and you hit it against one aux stream, and then you repeat that throughout the faceplate. Or you take one propellant stream and then you impinge two other streams of the other propellant. So that's the triplet. So the types that we looked at were the unlike pentad, which is 4-on-1, meaning there's a central hole and of one propellant, and then there are 4 holes surrounding it, each of which from each of which exits the other propellant, and they all impinge in the center. The 3-on-1 is the same thing, except with 3 holes on the outside. And then the unlike quadlet 2+2 or 2-on-2 basically means that you'll have 2 aux holes in line with each other, and then you'll have 2 fuel holes in line with each other, and they'll form a sort of plus configuration, and it will still impinge in the center. And so the biggest design considerations we had to look at here were the hole size of the impinging channels, like the final exit orifice diameter, because the holes are pretty small, so we need to think about manufacturability. We need to think about the elements, the spatial interaction with the igniter, because ideally you want the igniter to be integrated into the injector faceplate. And since we only had one element and that element needed to be in the center of the faceplate, it introduces problems with the igniter placement. And so you may, if you pick a certain type, you may have to integrate it into the combustion chamber instead. You'll integrate the igniter. And then finally, you want a symmetrical axial spray given a single element. So basically, if you were to take 2 streams and hit each other, then the resulting spray would not entirely be symmetrical. And so that's the reason we didn't look at that one. So as for what we actually ended up picking, we picked the 2-on-2, the plus configuration. And the main reason we did that was for igniter placement, because with that design, it allows us to place the igniter squarely in the center of the injector plate, and then you'll have 4 holes that surround the igniter hole where the propellant will exit. It's easier to integrate the igniter into the injector than it is the combustion chamber, and so we just decided to go with that route. In addition, the hole size is a little, and this is, versus the 4-on-1 and the 3-on-1, the 2-on-2 increases the minimum hole size that you need to drill, because with the 4-on-1 and 3-on-1, you'll have small holes on the outside and a larger hole in the center, but with the 2-on-2, they're more balanced. Got it. And so for the final high-level design decisions, you have to decide on your areas for the orifices. You have to decide on the angle at which they're going to impinge, and you have to decide on the distance that the propellant will travel before it hits the impingement point. So impingement distance is like a straight line distance. And so we use this equation on the right that is derived from Sutton, and essentially we know mass flow rate. You assume a discharge coefficient, and then you know the density and you know the pressure drop, and then you can calculate how much area, total area, you need for each propellant. And so, sorry, yes?
Sorry, can you, what is the required mass flow rate for each of them? Am I just impatient? That's
I don't have that written down, but Adam, you have the.
Yeah.
I think it's like point 0.4 and 0.6 or something like that. Yeah. 0.04 kilograms per second for fuel, then 0.06 for ox. It's around there.
Gotcha.
Really,
what?
Sorry, this is Alec hopping in over Chris. Do you know what material you're going to be building the injector plate out of?
We do, stainless steel. And
Okay, that'll be fun with that number 70 drill bit.
Yes. Wait, did you say it'd be fine?
Fun. That'll be very difficult.
Yes. Yes, and we recognize that, yeah.
What pressure drop did you assume across your injector?
So this gets into sort of the feed system related stuff, because we're assuming that it's the vast majority of the pressure drop is going to occur over the injector. Basically, we're not regulating nitrous. So as it starts from its vapor pressure at room temperature of like 51 bar, it's going to decrease naturally throughout the feed system. And so we assumed that it would enter the injector at like 45 bar and then decrease to 10 bar by the time it leaves.
Oh, that's not correct, I don't think. Well, like you can backsize your M dot with a known pressure drop, but we tried doing self-regulated nitrous, or sorry, self-pressurizing nitrous for HM8, and it was not a good decision. Like looking back.
Well, it's on that also to weigh mass throughput this one does. The self-pressurization is going to be a lot lower.
Yeah, like you're not going to be able to keep constant thrust, which for your guys's design isn't like too big of a problem, but what we found was like the biggest problem was we didn't have a shutdown purge. And having a shutdown purge to make sure that you don't have mixture ratio excursions during the shutdown event is super important. So would recommend having a regulated system with an explicit like nitrogen shutdown purge system, but like taking a 35 bar pressure drop across your injector does not seem like the move. It's like incredibly stiff at that point. Usually, like as a good baseline, you can find this in the injector chapter in Sutton. It's like 20% usually. So your injector manifold pressure should be around 20% higher than your chamber pressure.
Yes, that is something I encountered. And then we eventually had to change that. I guess we'll talk about that when we get to the, like, the feed system part will go slightly into more detail, I guess.
Like the nice thing about doing that, like if you assume a super large pressure drop across your injector, then your orifice diameters will end up shrinking essentially because your motivating factor is going to be your pressure, not the size itself. So by going to a more, in my mind, reasonable value for pressure drop, it'll allow your total area to increase, which means that it's easier to manufacture, and then you also have more flexibility in orifice arrangement.
Yeah, I actually, when I did the area calculations, I traded the 10 bar combustion pressure with like a 38 bar combustion pressure. And so you'd have like, I did this, the 20% thing, and the holes increased, but they didn't increase that much. I could pull it up, but it was like on the order of increasing from like 0.7 millimeters to like 0.9 millimeters in diameter. So we just decided that it wasn't necessary to go with a higher chamber pressure and or a smaller pressure drop.
Yeah, I'd be super interested to see your guys' calcs after this, just to make sure that we're like properly accounting for this.
Sure.
Because this is a pretty incredible stiffness, but like big takeaway, I think, aside from going with like a 20 to maybe 40% stiffness if you want, like that's pretty high, but you can make it work. Aside from that is like, do not do self-press nitrous. It was a huge pain in the butt. We tried like having to warm our nitrous to get the pressure up. It was awful. Would strongly recommend just going with a nitrogen press system or helium if you can afford it, but probably not, and then just regulating it down.
Chris, most of a second ago was that self-pressed nitrous should be more reasonable for the size and information they're looking at, especially if they use like a spherical tank instead of a cylinder. The self-pressurization should be more capable of handling what they're doing at these lower rates, just because you're not pulling too much of it at one time, but you will not be able to control it, like Chris is saying. So it'll at least be something to look into if you maybe want to add a little bit of regulation into it.
I don't disagree with that, but I think like with a more like future-facing approach and like being able to make it so that operations aren't awful for future engines and vehicles, like just start from where you want to end up. At least like this isn't like, yes, a rig is slightly more expensive, and yes, it is slightly more expensive to have to deal with nitrogen like a separate pressure bottle, but like it just makes sense to do it right from the first, like from the start, in my mind.
Yeah, I agree with that.
All right. Well, yeah, I guess we'll get to that later as well. Yeah, we have a bit of a feed system section later. So I guess I'll move on. Or actually, I didn't even finish this slide. Yeah, so created those hole sizes with that equation. The impingement angle, we decided on 45 degrees. I think usually it's 60 degrees, but 45 degrees is also acceptable, and 45 degrees allows us to fit the igniter inside, whereas 60 degrees didn't allow us to do that. So we're just moving on with 45 degrees. And for impingement distance, we found that the accepted value, you use the average of the fuel and aux hole diameter and then multiply it by between 5 and 7. So we took the higher range and multiplied that value by 7 and got 9.78 millimeters. And that defines like where the holes are with respect to the center of the plate.
You mentioned this in the previous slide, but wait, sorry, can you go back one?
Yeah.
All right, never mind. If you're going with the 2-on-2 plus, my point's irrelevant. Disregard.
Okay. Over to Alex.
We selected stainless steel for our material. Nitrous has corrosive properties, so we didn't want to like corrode our injector. It also has a similar thermal expansion rate to copper. It's also cheaper than copper. The main disadvantage to stainless steel is that it's pretty hard to manufacture. Yeah.
Sure. Okay. So with impinging injectors, very tried and true design method is with the stacked plate approach. Essentially what this means, you need to route your propellant from one inlet to potentially multiple outlets. And therefore you need to distribute each propellant through a manifold. And one of the easiest ways to create that manifold is by using separate plates. That in each plate, you'll have half of the channel manufactured, and then you'll have two plates, each with a mirrored channel, and then when you put them together, they form a full channel that the propellant can then travel through. And so this comes to like the big crux of where we are right now. We, as the injector team, do not have a single injector design selected. However, we have several candidates, and we have two specific trades that we are in the process of making, and essentially we'd like your advice as to which would be the best to proceed with. So the two trades are, we're trading between using 2 plates and 3 plates to create the injector, and then we're trading the way in which the propellant will enter the injector from the feed system. And so I will get into that.
All right, one quick note, if you go back.
Yes.
You said that the plates have to be like mirrored on each half, and I would say that that's not necessarily true. You can have one flat plate and then just have the manifold all on one side. Like you're assuming a circular cross section that goes through it, right? But if you make your cross section rectangular, one side can be flat, and then one side you just like take an end mill and then hollow it out. And like from a performance standpoint, you might take some losses, but I think it's going to be pretty negligible, like for this scope of the project.
Right.
And it would make manufacturing way easier. Also, like one thing that is going to be super hard for the plate style is actually getting proper sealing between oxidizer and fuel within the injector itself. Like if you mix in your injector, you will blow up the engine.
Yes.
Like it is not meant to take internal pressure like that. Well, yeah, like do not mix in the injector, otherwise you will like nuke your engine. Yeah. So like having proper sealing and redundant sealing is going to be super important in like drain passages, where even if you do get past one seal, you have a drain passage that allows that propellant to evacuate without mixing with the other propellant. All right, sorry.
Yeah.
I have a question on your material selection. So far you've been trading between 7075 aluminum, copper 182, and 3211 stainless. But why are those the only alloys that you're looking at? I mean, I know this is PDR, but like,
I'm not sure that's a question that I can answer. Is that?
I think that we had a few materials, but for the trade study, we only had 3 just out of like conciseness. We were trading between, I think, a bunch of different alloys, but in the end of the day, I think we only just put 3 of them on there. We can make it more concise, like in the future.
I guess, like, I think possibly Miles's point is that 321 is kind of an odd alloy to use. Like 304, I think is like a really good baseline stainless to compare against, because 304 is super like ubiquitous for stainless steel, like 304, 307 or something like that. But 321 is like I had to pull up MMPDS to even try and look at material properties for 321 because it's not as widely used, and then like a 6061 for aluminum would be a good baseline as well. 7075 isn't bad though, but like compared to 321 is kind of odd in my mind.
Yeah.
Same thing with the copper. Chromium copper is interesting.
Yeah, something else to consider is just procurement. Right? How much is it going to cost to buy it? Where do you have to find it? If it's an easier alloy to procure.
Yeah, I suppose the exact alloys will be a later decision. Or just general.
With the injector too, if you're going stainless, you can choose a softer one, so it's not actually meant to take that much load. Up your machinability, and you can still have a high chromium content.
I mean, if it's taking 35 bar pressure drop across it, they're going to need a high strength injector. That's also another reason to decrease your injector stiffness is like you essentially are going to have to treat it like a plate taking load from like a pressure loaded plate, and like 35 bar on a pressure loaded plate will end up having that plate be incredibly thick. So if you can just reg down and not just have these crazy losses. Also, if you have a super high pressure drop, I might worry about you guys. Like you mentioned being two-phase in the injectors, but I think you might end up just like choking and going full gas.
Okay. Well, thank you. We will look into that. Yeah, Ryan's got something.
Design on the materials selection. Just probably a good idea to double check the compatibility with nitrous. We found that 304 is actually not compatible with nitrous, but 316 was. So it's something that still statements that they do have different properties in different alloys.
Cool. Yeah, we'll look into that further and select one that an exact alloy that will fit all of our specifications. All right. Yeah, so I was talking about the traits that we were going to make, and I'm going to go into explaining one of them. And then the other will be explained within the actual designs that we show. We're going to show two designs. One design we're sort of leaning towards, and that's the design that is in the assembly that you've already seen with the actual combustion chamber. But for right now, we're considering two options. Axial entry, where the propellant is just manifolded straight from the top, and then it makes a 90-degree bend. And that's the top picture, and that's a section view. So that propellant will just go straight down, and then we'll make a 90-degree bend. And that is much easier to manufacture than the second option. And but what we're not sure about is, I know that when a fluid makes a bend in a pipe, you'll lose pressure. And I'm not sure if that 90-degree pressure loss will be too much. And so that's why we're adding a second possibility with the radial entry. So it enters from the side of the component of the plate and then is angled downwards. And the reason it's angled is so that it doesn't enter straight through the gasket and the oh yeah, I forgot to mention that we're sealing with gaskets for the time being. And so we have, if you have a several plate design or two plate design, between those two plates where you'll have propellant manifolds, you will have a gasket. And so that is what that black line in the top picture is. What
material is the gasket?
Graphite.
Wait, this is like a, it's not pure graphite, right? It's like a graphite mesh thing. I feel like you guys have used this previously.
Yes, I'm not exactly sure what the exact material is, but I know that the gasket material used in the prop lab is graphite, so that's mostly what we were basing this off of.
Yeah, for reference on that, for that graphite gasket thing that they've used has burned like 4 or 5 times in the years it's been there. They've had a lot of issues specifically with that. Are you talking about the bi-propellant on the left, right?
Yes.
Yeah, that one's had its own set of issues, so I wouldn't use that as an end-all be-all for high-end injector or high-end design capabilities. Yeah, go on. Sorry, that was just a note on that.
Oh yeah, fair enough.
Yeah, and wait, does Teams have functionality to draw on the screen? It doesn't, right? Pretty sure it doesn't. Anyways, for the coming in at an angle, it's just coming in.
You can do it on Zoom, but
there is a whiteboard.
I did not know where.
Yeah, there is a whiteboard. I don't know if it's going to be
all good. Like on the coming in at an angle versus coming in normal to the plate, if you go with the design that we chatted about before, about just machining your manifold on one side, then for your flat plate side, or even I guess the manifold side, you can just drill normal to that and then put a port directly into that manifold. So manufacturing is super simple there. I don't think that, once again, I would not try and maximize losses or minimize losses technically and maximize performance during this.
Yeah.
I think it would just be like keeping things simple for now, except that you're gonna have some pressure losses that you don't know about, and like that sucks. But you can also put pressure transducers downstream of that loss and just like measure your manifold pressure directly if you're really that interested in it. Instead of having to like try and go do like CFD, like which is the proper way of doing this. Like I think for the scope of this project, I would keep it simple.
Okay, so you would suggest the axial entry?
Yeah, and going to like manifold on one plate style. One other gasket material you can look at is I think a lot of people use copper. Like if you use like a C100, like pure copper, then it's super malleable and will kind of just squish into place.
Thank you.
Something else to think about.
C10 100 101.
Something else to think about as you trade versus a 2 versus a 3 plate is just complexity. So every plate you add, you're adding a lot of manufacturing complexity to it, where everything has to match up again and again and again.
And that's something we're going to address later, once you see the 2 plate and the 3 plate design, really. Yeah, I think that was all I wanted to talk about here. So I will hand it off to Alex, and we will talk about the 2 plate design.
Okay, this is our 2 plate design. I'm just going to move on to the advantages and disadvantages. If you guys have questions, we can go back to the images. Okay, so the strengths of this design, theoretically reliability. There's only one gasket instead of multiple, and there's fewer parts just in general. The main disadvantages of this design, there are small wall thicknesses, and we can go back to the images to look at those, and they are unavoidable, unfortunately. The geometry necessitates a channel being routed between the igniter hole and the orifice holes, and that makes things really complicated. And you have to use small channels, so we're in the 2 plate using 1/8 inch channels, and that brings up problems with the feed system. Yeah, it's hard to implement with our current feed system because we have an area restriction, which can, from the 1/4 inch pipes from the feed system, which leads to a pressure drop, and that makes things hard to predict. Yeah, go back. It's hard to see, but if you look at the transparent view, you can see up near the right, if you go slightly to the right of the igniter hole, right past the one of the orifice holes, there's a channel moving very close to that hole. And that distance there is very, very small, dangerously small. And there's another one right to the left of the igniter hole as well. Oh yeah. Yeah. So right here, and then yes, you can see that right here and right here. Although we can change this. This can get larger. That's the main problem with this.
Yeah, like you do have a small wall thickness there, but during operation, your like DP, your pressure differential across that should be like fairly small, assuming similar stiffness between the aux and fuel side. Right, like you have a small wall thickness, but you'll have high manifold pressure in both aux and fuel side that cancel each other out essentially, where your net stress is just like putting it into compression really.
Yeah, they're max.
But like,
sorry, they're still gonna feel that high differential during fill though.
Yeah. Right. It's like during your startup transient, I think is where you would maybe get bit. I think that the like it.
I'm talking like when they only have nitrous in the system and they're still putting fuel in, or vice versa.
Yeah, like during the startup transient.
Yeah.
It's also difficult to predict what the pressure of the nitrous will be because we're not regulating it right now. So we're not exactly sure what that pressure will be by the time it gets there.
Yeah, wait, so oh man, maybe this is I can wait until the feed system part, but like how are you guys pressurizing your fuel is a big question for me. Anyways, I don't think like there's like fairly complex geometry going on here. I think it doesn't need to be as complex as it is. Like we're trying to avoid losses, but I would probably just go with like hemispherical and keep it simple.
Maybe I'm just a I just have forgotten all my fluids knowledge, but is there a reason why you have your fuel injection points and your oxygen injection points opposite of themselves?
That's just part of the design that we selected. Like that.
You could solve that wall thickness problem just by having the fuel injection points adjacent to each other.
Miles. So
Yeah, I think that creates an unbalanced spray. It's not
exactly.
Okay.
That was the question that I ended up like going back on earlier. But yeah, if you have them opposite to each other, then your momentum ends up canceling itself out. So this spray goes axially instead of going off to one side.
Yeah. Okay, we'll move on.
So actually,
All right,
I
let's
have
get
one
one
more
more
kind of stupid question for the people on the call. Could I just have 2 input lines on the fuel and the aux? So instead of having to route channels, I could just do like a direct line and just get more GSE hose.
We were thinking about that.
But then we're trying to like upscale it for future engines. So the future engine might not necessarily work, like it might not have the same injector configuration, and we don't want to change the test stand. Like we want to make the test stand modular and be able to be easily updated for future designs.
I'm definitely a fan of keeping the test stand modular, but like the realized difference there is you have either test stand has a fuel supply and aux supply that, like, let's say you use flex hoses or whatever, like you hook up flex hoses here, which I don't actually see a port for anything to attach to, so that needs to be modeled.
Yeah.
But like, let's say that we go with like what Eric is recommending, like you just attach a T to the end of that flex line and then run hoses from that T to each of the individual ports. So it's like you still maintain some modularity for future design, but gain like quite a bit of flexibility. The problem then is like supplying, I guess, more fuel to one side, but you still run into that here, where the fuel manifold to that like closed injector hole is super short, and then the fuel manifold to the further injector hole is longer, so you'll have different flow losses between the two.
Hey, Chris, if they want to use this fire, they just get like a manifold block. Just put like 2 separate manifold blocks on there and just be like, okay, today I plugged 2 holes and like attach 2 hoses.
Yeah, and that's like essentially what you're doing with the team. Like a manifold block lets you have more flexibility.
Yeah.
To like, let's say you wanted to go with like 6 injector holes instead, you just unplug a manifold, or like unplug one of the holes in the manifold block and go from there.
Yeah. Okay.
What do you mean by manifold block?
I would have to draw that. Effectively, you've got your source line as a single, and then for a T is like your 2 outputs, but for a manifold, you can have like 4 or 6. It's kind of like for a high pressure line, you have a single input, and then you have several tubes you can just route out elsewhere. But that way you don't have to worry about a lot of the additional complexity about doing your rounded curves and things like that, because you're almost mandating that you have to, I think, CNC this. I actually don't know how you would.
We are CNCing this.
We'll talk about manufacturing.
But you could just do a direct line on all of those and just be like, okay, 2, 2, 2, 2, 2.
Makes sense. Okay. Right.
I got a question for people on the call. I don't know if they have any ideas, but is there a way you guys plan, or people on the call planning to model the compression of the gasket and just making sure there's enough of the seal as you get further away from the bolt line? That's what you guys heard about?
You can repeat it.
Oh, yeah. Is there any way to model the compression of the gasket just to make sure that we're going to be okay with in terms of sealing?
Especially away from.
Yeah, especially like away from the bolt line.
Yeah, so I think the like roadmap in my head is you can probably find the stiffness of the gasket from the manufacturer, and then wait, Ryan, you're ME, right?
Yeah.
Yeah, so then this just turns into like a bolted flange analysis. Like I think the critical point to check will probably be like with a certain preload and a certain manifold pressure, the deflection at the igniter, like in the center of the plate, you'll have the most deflection. So making sure that you don't lose preload on the gasket there, because your fuel and aux manifolds are going to be trying to like separate those 2 plates, and so it'll bow the middle out. And then if you lose compression of your gasket, then you'll get mixing of your oxygen fuel.
Yeah.
But yeah, like this just ends up turning into like voltage flame stuff, I think. Also, Ryan, it's hard to hear you. If you can move closer to the mic, that'd be great. Not important right now, but just a heads up.
He says thank you. All right, are we good to move on?
I think so.
Okay. So we're gonna move on to the 3-plate design.
Why is it not working?
I thought it was just arrow key.
I'm just clicking that. Okay, whatever.
All right, and then the second design that we were considering was a 3-plate design. It's a little bit hard to see what's going on in the picture there, but essentially the channels for the oxidizer are sandwiched between the top 2 plates, and then the channels for the fuel are sandwiched between the bottom 2 plates. And then we can head back to this slide if you guys have any questions. The main strengths of the 3-plate design are that it allows for larger channels, a 1/4 inch in diameter, because the channels are spread across 2 different planes instead of just one. And this also allows for greater wall thicknesses. And then a disadvantage is that it requires 2 gaskets, which is theoretically more points of failure. And then also, I guess, manufacturability is harder.
Yeah, can you go back to the previous one? Sorry. I think one benefit as well is that it makes it so you don't have like you don't have the same crossing manifolds, right?
Yeah.
Like for the single or the 2-plate design, you have to like weave both oxygen fuel in between each other, like Miles was talking about.
Yeah.
Whereas if you go to the 3-plate design, you don't have that. I think.
Yeah, because they're on separate levels.
Yeah.
Yeah, exactly.
Yeah, you should just be able to go straight line with that. Then you don't need to do the pairing like you guys have.
One, man, I don't know how I'm gonna be able to say this effectively. For the middle plate and the middle to combustion side gasket, what is so like you have the injector hole through the middle, and then you have 2 holes on either side.
Yeah.
What are those for?
Those holes are the other propellant. The other propellant is traveling through those holes after having been routed in the first gasket.
Oh, just kidding. Yeah, I'm silly. Sorry. Copy. And then it's just supply hole for the opposite gasket on the like top left hand side. That's just supply hole for the bottom.
Exactly. Yes.
Yeah. So the aux is routed down to the first 2 plates, and then it's split off and then routed down to the orifice holes, and then the fuel is routed down to the second 2 plates and then split off there.
Yeah. Like going back to the just machining 1 plate, like if you guys do settle on the 3-plate design, you could technically just have the middle plate be like take the complexity of everything and then just have 2 flat plates for.
Yeah.
Totally. Like head end and chamber end.
That makes sense. Yeah.
I said it. I just want to reiterate this. I said this on the 2-plate design, but especially if you go for a 3-plate, put some clocking features on these. Don't let your bolts orient everything.
Yeah, like having pins to align everything would be a really good idea.
Alignment.
I wouldn't do pins because you want to be able to disassemble this. At least I wouldn't do interference pins.
Yeah, I mean, I don't know that you need like assuming that your gasket has some correct tolerancing. I don't know that you need super good alignment actually. Now that I think about it, right? Like even if you have everything clocked incorrectly, as long as your gasket isn't allowing flow between your 2 manifolds, then you're probably okay. Is my gut feel.
I agree.
Would I, on the middle portion of metal there, to actually thread a line in, would I have to thread both that and the plate leading into it? Or could I through hole it, but at that point when my diameter is bigger?
You're talking about the bolt holes?
Yeah.
Thread 1 plate.
Why would you through hole it?
I'm just thinking about how you put it together. And how do you actually get all your fuel, like how do you get your fuel and oxides where they need to go? And on that middle plate, I think there's some complexity about how you have to get, is that your fuel or your oxide?
The middle one has both.
Both are,
Yeah, the
yeah.
top is ox and the bottom is fuel.
What is it feeding in at that plate? What's routing on that second plate?
The middle one?
Like, which face? Because it routes one on the top face and another on the bottom face.
That's a good one. Yeah, I have some concerns about how you would actually put it together in a functional situation.
I see.
But I think I have to like stare down and stare at models.
Yeah, and like going off of that, Eric, like going through hole to your injector face,
Right.
means that you now have a leak path that's going to try and like get past whatever bolt head or nut that you have inside your chamber, and then like climb all the way through your injector and out the head end.
Yeah.
Well, but the bolts aren't actually experiencing any exposure to the chamber because they're exiting through the flange. These bolts
What are the six holes on the injector plate?
The 6 holes connect the injector plates together as well as the flange of the combustion chamber. Everything is connected by those bolts.
There's a slide at the start of the presentation we can go to that.
Right, but are those not through holes all the way through all 5 parts there? Or do you have a blind hole in the top?
Oh, yeah. So the CAD has the CAD has through holes, but Adam did his calculations based on a tap joint. So we're probably going to change the CAD so that it's not going to actually, the bolts will tap out. They'll end within the top plate.
Copy, yeah. Like regardless of calculations for the joint, I think that would be a win in terms of like making sure that you don't leak and blow a bunch of fire back at your feed system as well.
That makes sense. Yeah, it's just something I forgot to change in the CAD.
Wait, I don't really understand that. Why do you want to put threads into the stainless steel instead of just putting a nut on the back face?
Like if you have a through hole through this stack, Miles, you'll have a leak path from combustion chamber to the head end.
Are all the bolts external?
Yeah, all
Combustion
these bolts are
chamber?
external.
They're external bolts.
But even though they're external holes, there's still a path through the gasket.
Oh, I
I
see.
see.
Thing is that you could still get fire playing directly
Sure,
back in your
okay.
feed system.
Oh, if the gasket bursts.
Gotcha.
Because there is an O-ring in between, on the bottom face of the bottom plate, there is an O-ring between the combustion chamber and the 6 holes. It's just inside the combustion chamber flange. Well, we have a whole interface slide later, and we will address that. Yep. Okay. I think we can move on now, and we will talk about the igniter.
Wait, sorry. I think like one of the things that you guys were trying to take away from the PDR was getting advice on 2 or 3 plate, right?
Yeah, that I did.
I don't know that we really settled on either.
I think we've given them a lot to think about.
Well, we settled one trade, which was the entry, and just for ease of manufacturability, we'll do the axial entry.
Yeah, I think that's applicable to both, right?
Yes, that is applicable to both. But yeah, what are your gut feelings about which 2-plate or 3-plate?
I don't know, man. I feel like if you guys can figure out a way to make 2-plate safe, it's probably easier.
Okay.
Yeah, from the manufacturing standpoint, 2 plates just superior because it's just in terms of all your manufacturability and having to put it together, you have so much less concern about alignment.
So are you guys gonna go over this later? But like, maybe you will. But who is gonna make this and where?
It's a great point. We have a little bit about that later.
Okay.
And then one last note on the 2-plate design. I think the only thing you'd really have to worry about is your minimum material condition for manufacturing on that. If you get too thin, you're going to experience some super thin walls. So just make sure to take that into account and double check it when you're actually manufacturing if you go down that route.
Okay. Well, thank you for giving us feedback. We'll take it all and make a decision. I like the channel manufacturing on only one plate and then keeping it flat on the other plate. I think that makes a lot of sense instead of the hemispherical. So we might change to that. Makes things easier. But okay, we'll move on.
Okay, so when we were talking about igniters, we kind of went through 4 main choices. We went through a spark plug, a nichrome sparkler, a hydrogen burn-off igniter, and a piezoelectric lighter. And what we ended up settling on was the spark plug is the best option, mostly because of its size. We found the smallest one to be about 0.23 inches, and like they talked about earlier, it has to fit in between the orifices, so that was honestly the main deciding factor. The nichrome sparkler we didn't go with because it's inconsistent and less controlled compared to the spark plug, because although it would have fit as well. And then with the hydrogen burn-off igniter, they typically have diameters of over 2 inches, so that just would not have worked with our design. And then same thing with the piezoelectric lighter. It was about 0.35 inches, so also just going to be too big.
Wait, sorry. Can you go back one? For the hydrogen burn-off igniter, I think that's for burning off the excess hydrogen.
Yeah.
That's like during the startup sequence, right? It's not used for actually lighting the engine.
Yeah. That was
Like-
more of an example. Yeah.
Yeah, like SSME and RS-25 use an augmented spark igniter, so it's like, I guess that's more industry use for the thing that you guys are leaning towards. But did you guys look at like augmented spark igniters? So instead of just using a spark plug, you have flow specifically for your igniter, so that you create a little torch essentially.
I've looked at augmented. Yeah, I looked into that a little bit. They seem pretty hard to build.
Yeah, so like I don't disagree with that. The problem is like if you run just a spark plug instead of an ASI, like I don't think that you guys are going to be able to reliably spark without like hard starting.
Yeah.
Because you need flow onto your spark gap in order to reliably ignite, right? And so like during your startup transient, if you just dump fuel and ox into your manifolds, you have to wait for them to go back up to your spark.
Yeah.
And then it'll light, and at that point you've already dumped a bunch of prop into your combustion chamber, and so you like create a bomb.
Yeah, we've definitely heard that too from the bi-prop lab here that relies on the spark plug, that the timing is pretty hard to get right. That's something we're trying to balance.
Yeah, so like the nice thing about an ASI is like as long as your thermal situation is good and you don't have like a thermal runaway situation, you can start it and then use that to like light your main prop instead of trying to wait until it like reaches your spark gap.
Yeah, definitely.
So something to look into. Other thing that I think a lot of college teams use is just like the aluminum oxide sparklers that you have for 4th of July or whatever. Like you can stick that in the chamber and then use that to light.
Yeah, that's like the nichrome sparkler, I think, that's what we were, Paul, I think, advised us to use. But, yeah.
Gotcha. Is that, okay, maybe I've misinterpreted that. Isn't nichrome usually like just the wires that you use that you apply like a voltage across them?
Yeah. Is that not what you're saying?
No.
No, I'm talking about like
Oh, okay. Interesting.
Like actually.
Oh, okay. Okay, yeah, well, I guess we can look into that too.
Problem.
I thought that was just what you guys were calling it because your previous uses includes fireworks on that row.
Yeah, I think they're talking about like the e-matches for that. But yeah, like one of the problems there is you can deposit aluminum inside your chamber, but all right, sorry, I'll let you guys keep going.
So if we do use a spark plug, we found rimfire spark plugs, which are available for purchase, and they fit between our 4 propellant orifices. And the pressure and temperature ratings have been verified through our existing Cal Poly bi-prop lab, which does use spark plugs. That says 6 millimeters, but that's roughly 0.23 inches and will fit in our design.
I would talk to Cody about his experience using that spark plug because I think he hates it.
Okay.
In my memory.
He hates it. He hates it.
Yeah, those spark plugs for the one in lab also have to be modified to arc to the wall, if I remember correctly. So Cody does have to go in and like cut the tab off.
Yeah, that sounds about
And I
right.
think that's part of the reason he hates it.
Sorry, like just one comment on the design process here is like, this should not be like the interface between the injector and the chamber. Like you guys are two separate groups working with each other. This should not be the injector team passing you a hard requirement and then you guys having to abide by it. Like if you guys can get a significantly better spark plug that has to move injector holes, that's something that should be in the trade space, I think. Like maybe you guys don't end up going with that, but it's not something where they should just be able to say like, I 100% need this, and then it's taken as gospel truth. Like there should be a back and forth between y'all. Like you are both equally contributing members to the team, so it shouldn't just be like one team passing direction or passing requirements one way without any consideration for their downstream effects.
Also, you make sure you know what kind of pressure ratings that these can handle, especially across those threads, because I see straight threads with fluid system and I get spooked.
Yeah, I mean, it's 150 psi chamber pressure, so it's like probably not too bad.
Oh no, but definitely check it.
Pressure should be fine. Yeah, for sure.
Okay.
Sorry, one last thing.
Yeah.
Like, how would you be sparking the spark plugs? Like, you need a high voltage source.
Yeah.
That's like oscillating at some frequency typically. One thing that I've done is like you can buy like power supplies for neon signs or whatever and hook that up. But something to keep in mind is that like you can't just throw a spark plug in there. You do need to apply a voltage across it.
Yeah.
So that's something to consider for CDR.
Yeah, definitely. I think that.
And like,
go ahead.
And especially if you're going to be using that as like timing critical things in the ignition sequence, like you need to have that hooked up to your control scheme.
Okay. Yeah. Yeah. Our test 10 people might have something on. Nope. Okay. Maybe they don't.
I mean, my thought was we could get a coil and a battery, and I'm not entirely sure if we can get it to spark with that setup, but we could probably come up with something that would allow it to like actually spark or just a continuous arc.
Yeah. Yeah, the problem is like you need to really oscillate. Typically, you can't just like apply voltage and hold it there. So looking into like neon sign and power supplies would be, it might behoove you.
Yeah, write that down. Neon sign. Cool. Okay, thanks. All right, so this is the interface. It's pretty simplified here. All the equations are in the appendix, but I initially just treated it as a tapped joint for the reasons you were talking about earlier, and because we weren't sure if we could fit a nut on the top face of the injector as well. I think I go into that later. But I did an analysis to choose the minimum bolt diameter, picked one that was a little bit bigger with a number 6, 32 bolt. And then I did an internal thread shear analysis, and this is just from Shigley's of a bolted flanged joint. And I focused on the shear of the copper itself of the internal threads because those are the softest. And even with a factor of safety of 2, which we should make, which is really high, it was only 6,000 psi on those bolts, and the shear value of copper.
Sorry, can we go back a couple slides to the injector design, and you can show me where the copper is? I thought this was stainless. I think I misunderstood something.
There.
Oh, perfect. Gotcha. Isn't that oh, you're saying we're flipping it and threading from injector face up now?
Yeah, that's what we were.
Hey, by the way, 632s are like one of the worst screws to use for like thread strength.
Okay.
Because they have a really poor shear area compared to like it's the shear area versus I think the thread engagement. just because of the depth. So I would up or even downsize and increase the number of bolts if you can.
Okay. Yeah.
And then
I'll,
what were the?
What's up?
Go ahead.
No, I was just saying that the joint analysis that I did in Shigley's assumed that the bolts were coming from the top of the flange, which the headed joint on the combustion chamber itself. I would assume that you can flip them, so they don't have to be coming from. That is like harder to manufacture, I guess. So.
Yeah, I mean, if you end up going with the like just buy 3.5-inch stock and then don't machine it at all, you're gonna need to install from the other side, right? Like from bottom to top in this picture here.
Yeah.
And then you just like have a blind hole that's tapped. What was your load that that is being applied to the joint here? Like how did you calculate that force?
Yeah. Let me go back. I don't know. I tried to simplify it down a lot. Let me grab. I have that. I did it based off of the internal pressure and the thrust.
Internal pressure of what?
Of the combustion chamber. Now that thinking about it, I probably should have accounted for the pressure drop on the injector itself. I didn't do that. I just did it based off of the combustion pressure within the combustion.
Yeah, so you just did like the blow off load of like pressure times area of the combustion chamber at max material condition.
Yes.
Or sorry, minimum material condition, least material condition.
Yeah.
Okay. Yeah, I think like it gets more complex because you're gonna have, if you're like having this plate stack up, you'll have internal pressures within the plates applying blow off loads in there as well. Like trying to cause internal gapping, so it'll be
we recently just changed the design to that these bolts would actually be holding together the injector like in the last few days. Originally we had the injector having its own set of bolts, so we have to trade that a little bit more and see if these bolts can actually hold together the whole injector.
Gotcha. Definitely something to look into there. And then
what? You guys go forward really quick.
What's up?
You go forward one slide really quick.
Yeah.
Those look like flathead screws. I'd use a bolt.
Yeah, those are pretty.
Like an Allen wrench head. Hex head.
Yeah, I was gonna ask what material your guys' bolts are.
I think we're just gonna do stainless. I was only worried about the shear of that copper, and stainless, it's a lot stronger. So I didn't even really look. I assume the bolts were stronger. The shear were stronger. But
I think that's.
And how are you guys using that O-ring?
Sorry, I missed that.
How are you guys sizing that O-ring?
We have O-ring sizing.
Using Parker.
Yeah, we're gonna use we're using. We use Parker, but it's kind of we haven't picked the exact O-ring yet. But
okay.
Yeah, we're just gonna use the Parker handbook.
Okay.
Cool.
Yeah, I would just say to probably use like A286 bolts for this.
Okay. 8286.
A286.
Oh, okay.
And then like going back to Miles's point, maybe you just end up using quarter 20s or something like that.
Okay.
Or 1032s. Like I don't think like the proper way to design this is perhaps to try and like get a stress value that's right, like super close to yield and ultimate with your factor of safety is applied, but like realistically you can just slap some quarter 20s on there, have mondo margin of safety, and then roll from there.
Yeah, that makes sense too. Cool.
You have red shear on copper on the last slide, but it doesn't look like it's threading into the copper here for a lot of easy reasons.
What's up? Yeah, I would assume the copper is threaded here. Does it not? Does it just not look like it? I don't know. Maybe the CAD doesn't update it specifically.
Are you saying that it's threaded all the way down?
No. No.
The bolts have.
Oh, bolts flip. I'm confused.
You float the bolts, or else you're going to end up with a lot more leaks.
Yeah. I think we're gonna flip the bolts.
No, float them. don't thread anything
Yeah.
between your first and last sections.
Yeah. I was confused a little bit with the question.
Yeah, also, I don't think you should have a fully threaded bolt here necessarily. I think going partially threaded is fine, especially if you're floating them.
Okay. Okay.
Like you shouldn't, like this joint should not have to carry any shear through it, but yeah, I just don't see the real benefit of using fully threaded. And then also, like going back to the load case, I think you have to apply a moment to the joint because of the internal manifold pressure.
Oh, really? I didn't. Okay. Because the manifold pressure, you have to apply a moment. Is that what you said?
Yeah, like each of the individual fasteners is going to see a moment because your manifolds are going to be trying to like bend the plates out
Okay, that makes
from
sense.
the manifold, which then applies a moment to your fasteners.
Okay. Yeah, that makes a lot more sense. Yeah.
I think it should be pretty minimal, but just something to double check.
Okay. Yeah, I'll look into it. Okay, cool. All right, now Nick is going to talk about the O-ring a little bit.
Hello. So talking about the O-ring, we had a few requirements that we wanted. I chose that it would be a static seal, and it's going to be an O-ring placed in a face seal groove. It will withstand pressures of up to 10 bar or about 150 psi, and the material, which is still to be determined, which we're like figuring out still. If you have any suggestions, we'd appreciate that. Should be inert with ethanol and the nitrous mixture, because we don't want it to corrode. It would lose its functionality, and able to handle the high temperatures during the firing. Hopefully it doesn't melt, so it stays functional. Yeah, and then for being a static seal in the O-ring placed in a face seal groove, I chose a face seal groove and a static seal because, as you can see in on the right side, the manufacturing is pretty simple. We just kind of have like we can just turn it on a lathe. We'll have 3, which shows like a diagram 3 shows like a face seal, the groove of it, and then 4 you can see there's just the O-ring fitted in it, and then it will be bolted together. Yeah. Any questions or any suggestions?
Just to clarify, so this is an additional seal from the combustion chamber.
Right, in between the injector and the combustion chamber?
Yeah.
Can we go back one?
Go back one?
Yeah, please.
That's very well.
Gotcha.
Okay.
Yeah, I mean,
I just
think
left
what you
everyone in there.
could do is instead, yeah, if we go to the next slide.
Yeah.
I don't think we need to do like an elastomer O-ring. I think you could probably get away with doing a copper seal here and then just using your joint preload to compress it, and then you don't have material compatibility concerns. And then you also have like decent performance at high temperatures. Also, you mentioned like turning it on the lathe, but I think that's showing that we're like it's like milling it. One thing that if you do mill it, you have to, and I guess for lathes as well, like typically you want to polish it after the fact just to make sure that you have good performance, because like you'll have machining marks on your sealing faces, and so you'll have like these, you know, like 1 thou deep grooves going from like where the chamber is out. How do I say this? It'll be like radial direction, and that can allow leak paths past your seal. So typically you want to try and like have some polishing on that surface to help lay those down.
I think an elastomer would solve those problems, though, wouldn't it, Chris?
Yeah, but then you have to deal with like material compatibility and temperature concerns. And like I think the copper, like depending on your joint preload, it will smush in a decent amount. And also it's like it's probably sufficient, especially considering the low DP across it. But I want to instill some good behavior for industry.
I mean, O-rings, elastomer O-rings are relatively cheap. You could just replace them between every fire if you really needed to.
Right, but if it melts during run, I guess with 3 seconds it might not be a concern, but like they're using copper, which will have a super high thermal conductivity. So like it will definitely get hot. So if it leaks during run, you're gonna blow combustion chamber out your head like we did for HM8.
Yeah, that's fair.
I don't know. I'm not super tight with the copper, but it's like pretty cheap. And if you're not planning to take the injector off the combustion chamber often, like you do it once and then forget it, hopefully.
Can you buy COTS copper O-rings? Because making those would not be that fun for most of the tools they have at Cal Poly.
I think you can. We also have a water jet now at Poly for what it's worth.
True.
So like, you can buy some 1/8" stock, do like a 100 thou channel or something like that. I don't know, just something to look into. I know a few teams use copper instead.
Okay, speaking of choosing elastomer or copper, I chose to do my study kind of on more like elastomer seals. So move on to the next one. You kind of see like how we chose, like why I chose an elastomer seal was because like Parker O-ring like kind of gave like a whole graph on choosing elastomer seals specifically, and I was also looking at studies from like Sandia National Laboratory, and they used exactly this ethanol and nitrous mixture, and they used fluorocarbon. I think it was fluorocarbon elastomer, and they said that that was working pretty well for them. And yeah, so that's why I just continued through and just used Parker O-ring handbook for using elastomers O-rings. Yeah, so before we had an inner diameter groove of about 2.28. And looking in the Parker O-ring handbook, I kind of looked through and to see like the inner diameters of the O-ring sizing. And I found that the O-ring size number in the Parker handbook for 228 was the closest to what we had to 2.28. So after I kind of went back and forth with Adam on the face seal, and we were like, okay, well, it's better to go a little bit smaller because we don't want to run into the bolts, the holes over there, the bolts. So we ended up going with 228 instead. So after we had an inner diameter groove, and we decided on 2.234 for that O-ring number of 228. Furthermore, on the seal dimensions, the actual seal dimensions, we found that can't really see. Okay, I'll look on the side. Okay, for the numbers between 208 and 284 stand at a cross section of about an eighth nominal of an inch. And the compression ratio ends up being around 20 to 30%. And from University of Akron, they said they used for their static seal in a face seal groove, they used around 20.8 for that. So I thought it kind of matched up. It was good. I don't have the exact numbers yet for the cross section O-ring and the gland depth calculations just yet, but I do know that it lies somewhere in this. So that's how I did my sizing. Is there any suggestions or anything for that sizing method?
Wait, sorry, what was the university thing you were using?
Akron, yeah, Akron. My bad.
But what value are you getting from them?
They got 20.8% for their squeeze percentage, and
yeah, I think like the Parker O-ring handbook where you're pulling these from, like on page 4-18, it looks like it specifies the gland that you should be using with these.
Right.
So I would probably just go with Parker's gland design, and then also would double check, because I've screwed this up myself multiple times, is like I think there are different sizing for internal pressure versus external pressure. So just make sure that you're using the internal pressure ones. It changes it slightly.
Right. I believe for internal pressures, it'll be more towards the seal will want to sit towards the outer edge, because we want it to kind of push into the wall instead of like starting on the inside and pushing out. So I'll have better functionality. So yeah, thank you for that suggestion. I'll use the gland depth for the Parker handbook. Thank you.
I got one comment, which would be just, you've done a lot of work to like size this, but as your design matures across the whole system, just don't be afraid to upsize or downsize the grooves. The other thing is, what factor of safety do you have on your pressures? Because I see you're just using the chamber pressure.
Oh, right. I'm not sure yet. Do we have a factor of safety for that?
It looks like everyone's been using like different ones, and I think we should make it a little bit more consistent. for like the joint, I was using 2, but for like Jake was using like 1.15 or something. Yeah, so I think we need to. Oh, okay. Yeah, I think we need to make it a little bit more consistent.
As long as you got something.
I mean, yeah, like so you can either apply the factor of safety to the loads that you're inputting, or you can apply them to stresses. And I think it sounded like Adam was accounting for the factor of safety there. Also, Adam, the real blow off area that you should be using is the seal diameter instead of the chamber diameter.
What?
Because like,
Why
if
is
you have
that?
leakage past your chamber to injector interface and it stops at the seal, you'll pressurize the entire seal area, which is like, obviously you can see it's significantly larger.
Yeah, I didn't know that.
You should be using that instead.
Okay,
So
thank
like
you.
the conservative way of doing it would be using the OD of your seal gland. Which you can see here is like, 1.5 ish. So you're gonna have like twice as much blow off area.
Yeah, definitely. Okay, yeah, that's very helpful. I didn't know that at all.
Okay, and I think Ryan had one more thing to say.
Yeah, I was just wondering how you guys chose your O-ring cross section, like whether it's 100 series, 200 series O-ring. I know you get the same OD for such different cross sections.
Okay, did y'all hear that? Okay, I'll repeat the question. Ryan's asking, how do you exactly choose what kind of cross section area that you want for your O-ring? Like, did you just go with like a series? Did you go with how much pressure it goes with? What did y'all choose to figure out the cross section for your O-ring?
Are you guys doing heritage design? Is that the question?
Yeah, I think so.
Heritage design?
Yeah.
Oh, I thought Ryan was asking our presenter.
No, I was asking y'all if that's okay.
I think.
Well,
so we would always choose our own. So these all look like they're pre-made, but we would just buy like a length of material, and that would just create as many as we wanted. And those traditionally just come in all round stock.
Okay.
Don't do what we did.
Quick masters.
Yeah, don't do that. I think Ryan's question was more like essentially selecting what cross sectional diameter.
Yeah.
Yes.
Like, I think Parker has maybe possibly pressure ratings, but also for this joint, like 150 psi is going to be pretty easy as long as you get the proper compression.
Right. Okay. Yeah, that's why I use the this dimension for they designed for up to 103.5 bar, which is about 1,500 psi. So I was hoping that would be safe. Yeah.
Yeah, exactly.
Sweet. Okay.
Man, I'd roll.
That's it.
Thank you. All right, let's keep going. All right, then this is, sorry, Miles, this is our very wimpy looking manufacturing method slide.
It's not even the right lab, dude.
I don't know how we did that. All right, yeah, so for the combustion chamber specifically, we're gonna like turn to get the outer contour, but now that you guys are saying that, we should just make it really, really thick, not care about it as much. Maybe just for like material, for manufacturing, like efficiency, we don't do that. But then I bore out chamber hole and then just use a manual mill to face the holes on the outside for the flange. And then we're trying to talk to CNC lathe operators to get the match the nozzle contour within the chamber, because we don't want to deform the copper because it's so soft, like fixing it too hard. So yeah, very bare bones right now in terms of manufacturing method. We need to kind of flush this out. So any suggestions would be greatly appreciated.
Thicker material will also crush your copper less, so it'll help with your contouring.
Yeah.
Yeah, Ryan, do you have your blue tag?
Try to get it hopefully by the end of this quarter. So not fast enough.
Yeah, he's trying to get it right now.
Sounds like you'll be machining this hopefully. Like this seems like a decent blue tag part too. I don't know.
Yeah.
It's actually super expensive now that I think about it. Maybe don't do this as your blue tag part.
Yeah, but our manufacturing lead has his blue tag, but he's not certified to do the CNC lathe, and I don't think he plans to be. So we're trying to talk to people that he knows that are CNC lathe certified here. We don't have anyone for that yet, and we need it.
Yeah, I mean, you can like go to the shop techs and do fee for service, but I think like one of the really nice things about doing this is like doing it yourself.
Yeah,
So,
yeah.
If it's in the timeline, would strongly recommend that you train someone up and like have shop techs train somebody up, because I think it'll help make the project more fulfilling.
Yeah, definitely.
But if it becomes critical path and it's gonna like push you back multiple months and you're just like waiting on this one part, then yeah, like probably just do fee for service for the shops.
So manufacturing is cool, but do you have a way to verify that what you manufactured actually meets your designs and drawings?
Like testing and everything?
Like quality measurements or testing?
Yeah, we don't have that fleshed out now, but we certainly will once we actually have a method to manufacture it a little bit more planned out.
Okay, I just asked because this is a specific contour, and measuring that without something like a CMM is pretty difficult.
Yeah. Our manufacturing lead was talking about a I don't know what he was calling it forming. Like you put a piece inside of the copper. Yeah, and talking about doing that, like the exact contour of the chamber itself. But it seemed really hard to do to get like a.
You're gonna make a form tool the entire size of your chamber?
No, just for like because there's a specific part of the chamber, just the throat. It was like, I think it was only the throat and then like part of the nozzle. So our nozzle is almost linear.
So just the diverging section.
Yeah, just a specific section, like bore it out and then just have a specific section for the contour be a forming tool. So we were thinking about that, but that seems pretty hard to. We have to manufacture like a cutting tool like pretty precisely, and that seemed.
And then you got to measure your cutting tool.
Yeah, exactly. So.
Yeah, like if you guys are going with a straight diverging section and like conical nozzle, I wouldn't worry about it. Like we're leaving efficiency on the table already, so like any deviation from the nominal throat radius to conical transition is like kind of gonna come out in the wash.
Yeah, that's what.
And like contracting section is pretty unimportant. Like you can definitely take deviation there.
Well, I mean, I didn't know that. Why is the contraction area not
I mean, like the contraction part of your throat is really just trying to get it to Mach 1.
Okay, so you're saying like that contour that we get, as long as it gets to the throat diameter, and like not a straight cutoff, it's okay.
For what you guys are trying to do, it's fine.
Okay, that's what I figured. Cool.
All right. Okay, last note, just buy double material.
What?
Or more.
What do you say? Buy? Oh, buy double material. Oh yeah, we will. Yeah, we're not gonna one and done it.
Yeah, we're also planning on practicing with whatever aluminum stock that we have to try to, because we have leftover aluminum stock from past years, and also it's obliged to manufacture aluminum. So at least trying to make all of this at least once before we're trying to make flight or test.
Yeah, definitely. We need a lot of practice manufacturing. I think most of the people on the prop team have red tags, me included. So, yeah. Sorry, Chris. But yeah, we're going to turn it over to Alex.
Yeah, so all the injector plates can be made on a 3-axis mill, but on making stuff on a 5-axis would be a lot better. For the 3-axis, we'd have to make like a fixture to do those 45-degree holes. We were going to use a ball end mill to do all those channels, but if we change the flat and all like a rectangular channel, then we'll just use a flat, and then just various twist drills, and the 60-degree chamfer mill will be used to make the area restrictions and the actual orifice holes. And then again, twist drills will be used to cut the bolt holes, the hole for the igniter and the feed holes. And then the gasket we were thinking was going to be cut via laser cutter, but we weren't actually completely sure about that one.
If it's copper, I don't know if it'll cut on a laser, especially CO2 laser.
Okay.
I could be wrong on that, but double check that.
No, I'm pretty sure that's right. I think you just reflect the beam back. I think you would just go with water jet at that point and then polish it after to make sure that you don't have like a ton of garnet stuck on it.
So are you guys cutting? Are you guys using the same diameter tool as the as your contours?
Yes, that was the idea.
Don't do that.
Okay.
You're cutting steel. You're going to be generating a lot of heat. Use something smaller than the size of your channels.
Cool.
And yeah, like you talked about before, I'd go for the one-sided plate design too for manufacturability. And then you can use a ball end mill if you want for that, but you can also just use a rectangular.
I think changing to flat would just make things easier for everything. So I think we'll just do that. Yeah. All right.
Yeah, and so then I'm coming back up to talk about the feed system. And so this is kind of getting in between ground support and the test stand design and here on the prop side. So the feeds, in terms of the feed system design that has been completed so far, this preliminary P&ID is the basic idea. And the physical design of this and how this will be translated to the test stand is going to be talked about more in the ground support's presentation, which is going to be immediately after this. But the basic idea is that we still have, as was discussed earlier, the nitrous will be self-pressurizing, and then the fuel, so the ethanol, will be run off of a nitrogen pressurization system. And so then that will all then be feeding through Venturi's so that we can measure the flow rate, and then feeding into the injector. A lot of the decisions made here, there's a lot of the components were made with safety considerations in mind. Convincing the school that we can do this safely is kind of the biggest impactor here. So each of the tanks will be outfitted with overpressurization devices, so dump valves, pressure safety valves, and burst discs to prevent any overpressurization in the feed system itself. Right now, on the ethanol fill is planned to be done manually, but then because there is work that's been done on previous hybrid rockets as to autonomous nitrous fill, we are trying to adapt a lot of that work to be able to be done so that nitrous fill can be done remotely without any operators near it, because that has been shown to be one of the most dangerous. Having flowing nitrous is one of the most dangerous parts of using nitrous. So minimizing the amount of people who are around flowing nitrous is of utmost importance. And then kind of moving down to the actual feed system from the tanks to the engines. The number of valves has been trying to be minimized just to run costs down. The addition of extra effectors will drive up the cost. But at a bare minimum, we have overpressure devices to a safety valve on each side, the nitrous and the ethanol, and then dump valves so we can manually dump fuel on that side, and then running into our main propellant valves, which are the ones immediately preceding the thruster itself. And then it has also been instrumented with, I think there are a total of 9 transducers right now for measuring the pressures as we see fit. The actual instrumentation part of this will be modified more as we kind of go in and are deciding more of what measurements we want to be taking of the engine. But at a bare minimum, we're looking to measure the combustion pressure at some point. That so far has not been included in the combustion chamber CAD itself, but that will be planning. We're trying to figure out a way that we can plumb a line into some sort of tube into the combustion chamber to measure the combustion pressure directly to measure the performance, and then everything above that is more for safety, other than the transducers on the venturis itself, which are measuring flow rates, and then the other two are just for ensuring that all of our line pressures and tank pressures are within spec. And this will all be routed through the DAC system, which is going to be talked about more in the test stand. And with that,
all right, can we? Sorry, that was a lot.
I know.
Did you say this is going to be talked about later? Like
somewhat. Most of the specific design, the specific component sizing and selection is planned to take place between now and CDR once we have our flow rate. Right now, I think the plan is to use 1/4-inch piping and running out of the feed system, because one of the considerations with this is also scalability and being able to use this with larger engines that are going to have higher mass flow rates. And that's one of the considerations that we're still kind of unsure about, is how we have an oversized feed system running on such a small engine, and what kind of complications that's going to bring up. So that's one of the biggest things that we're trying to work out between now and CDR.
Yeah, it'd be great if you had some sort of valve that could let you adjust down to lower pressures to be more suited for a small thrust engine. Sorry, I'm being snide. Okay, so overall, I think like the safety aspect is pretty decent compared to what other folks have done. I'm not sure I understand the need for PSV 202. Like PSV 201, 202 should be like seeing roughly the same pressure, right?
Yeah.
And so like I think PSV 202 is probably not required. Like if you can relieve the ullage of with PSV 201, then you'll get like a direct pressure drop with PSV 202. And then yeah, I guess the ethanol system doesn't have it. For the venturis,
yeah, the main reason that one's on there was for fill operations, in case there was I'm not sure if it was necessary either, but that was mostly I mostly included that just in case there was some sort of blockage in the tank itself, where there was an overpressure event between the nitrous supply and the tank, but I'm not sure if that's entirely necessary.
Yeah, I don't think that failure mode is like super likely to happen personally. So I think like I would probably challenge requirement for 202. For the venturis, like what pressure, I think you said you haven't decided what sensors you're using, but like we already had some standard pressure transducers for CPSS. Like, are you guys going to be trying to use those again or buying new sensors?
Yeah, we're planning on trying to reuse as much as possible. But yeah, so that's the basic idea, is trying to adapt as much. And that's why we're trying to not prescribe as much for like what exactly we need, and trying to see if we can modify what we have. Because we do have a lot of equipment that's still functional and that we just need to check out.
Yeah, I think if you guys are going to end up buying new deucers anyways, like the venturis, you're using 2 static deucers on, it looks like one at inlet and one at throat.
Yeah.
The actual DP between the inlet and throat is typically like pretty small for a venturi. And so like, you subject yourself to the noise of both your inlet and throat pressure sensors.
Right.
By using a static transducer, or like a static pressure transducer. They make these things called DP transducers, which takes the difference between both sides of the diaphragm instead of having one side of the diaphragm be vacuum. And so those are way better at measuring small pressure differences. And so typically for venturi flow meters, you'll run a DP deucer between inlet and throat instead of 2 static deucers. So like, I think if you guys have to buy, this is fine. Well, I don't know, I have to look at the actual pressure ladder to make sure it makes sense, but this is probably okay to run with static deucers. But if you guys are going to have to buy new deucers anyways, then getting a DP deucer for the venturis would be probably in half of a better direction. Mm-hmm. You mentioned trying to find a way to get a hole into the combustion chamber. I will point out that you already have a bunch of holes coming into the top of the combustion chamber, so possibly looking into just tapping off through the injector plate, and then measuring static pressure at the injector face is probably an acceptable estimation of chamber pressure. And then like what pressure is GM2 supply going to be at?
So that's the other. I think right now we're planning on, because in one of the first iterations we were planning on regulating the nitrous and the ethanol both with the gaseous nitrogen, and so we were planning on having them at the same pressure anyway. So right now I think the idea is, because I'm not sure, because Aiden, this is kind of also an injector question of what supply, because I was, from what I heard from the injector team, he wanted them there to be as little of a pressure differential between the two as possible. So the idea right now is to still have it regulated at around 750 psi, but that is still to be confirmed.
Gotcha. Okay, yeah, I think like, and that's just using one of the regs that hooks up to a K bottle.
Yeah.
How do you? And then you control flow with just your main valves, right? Like prior to test, you open the PS or PBS PB 101, I think. Sorry, it's kind of blurry. So okay, so you open PP 101, that pressurizes the ethanol tank, and then your nitrous is like self-pressing.
Yeah.
And you fill with HR 201, and then like when you go to fire, you open. You have two PV 101s, or am I misreading that?
The blue line is, they're all 5s, so it's 501.
Oh, copy, thank you.
Yeah.
Sorry. Okay, so like your startup sequence looks like just opening PV 101 and PV 201 and then using pressure.
Yeah.
Right. Yeah, I think like, man, I would much prefer to just run regulated nitrogen into the nitrous tank, I think.
You need a way
that
that you can purge it anyway.
Yeah.
Yeah, and that's another thing, is you probably want to run nitrogen into like maybe directly downstream of your main fuel and main aux valves, so that you flush out your nitrogen, or like you flush out your manifolds.
Yeah. Yeah, because that was in one of the earlier iterations. This has kind of been pared down for complexity of manufacturing. So, because that was one of the concerns, was having the ability to flush downstream, and it was kind of unsure of kind of what pressure of the nitrogen, how many regs we would need on the nitrogen if we wanted to blow the same 750 psi nitrogen through as the purge, or if we wanted to reg it down even further to have it lower pressure.
To do a purge run, you would actually do it at your supply.
Okay, that's supply pressure. Okay.
Yeah, you could also just run an orifice, Eric. Like you run from 750.
Yeah.
Supply pressure, and then like valve, and then orifice it down so that you get whatever.
Yeah, I mean but you save yourself a valve by not doing an orifice, right? Because you're gonna have to control its supply anyway. Because what we would do for those test runs is that we would go to 50, hold, go to 100, hold, go to 150, hold, then purge. And then after, all you would have to do is reopen the supply, right?
Oh wait, sorry, I think I might be thinking of something else.
You could orifice, that's not wrong, but it's cheaper to just do it at the supply bottle because you're gonna have to do it anyway.
Yeah.
Yeah, like if you're worried about overpress, orifice is probably the way to go. But yeah, if your manifolds can take it, then it's probably fine. Yeah, so purges for downstream of main valves, so that way you can flush out your manifolds during startup and shutdown.
Yeah.
Pressing nitrogen tank, looking at whether you actually need PSV 202, and then deproducers on Venturis. And then, other than that, I think it looks like fairly acceptable.
Mm-hmm. Yeah, the biggest thing is definitely going to be sizing and ensuring, because I know so the CV for the main propellant valves, I think, is going to be one of the things that I'm have the most questions about. If oversizing it is going to cause issues running into the injector, but I
think it's easier if you just, if you're worried about oversizing, just put a reg on it.
Okay.
And just reg it down. And whenever you scale something up, you either just eliminate the regulator in the system, or you just change what your reg is set to.
Yeah, I mean, like oversizing on CD, unless you're using it for control authority, isn't like too big of an issue. It's essentially like as CD goes to infinity, it's essentially just like removing the valve, like if you just had a straight section of pipe there or two. So like, I don't think during run you should be taking a large pressure drop anyways. Like if these are ball valves, like ball valves will essentially act like a straight pipe or straight tube. If they're full open, and if you're running, that's another thing. Like, how are you controlling these valves? Are these just pneumatically actuated?
Yeah. So the main idea is to have for the dump valves is to just use solenoids, just straight solenoids, and then for the actual main propellant valves to use pneumatically actuated ball valves, so that we have that kind of straight section of pipe. And to minimize, but for the dump valves, it's not as important. So that's, those are the main considerations for the.
Wait, sorry, dump valves, are you talking electric or are you talking pneumatic?
I was thinking electric solenoids for dump. Sizing them appropriately might be an issue depending on how fast we need to dump. That is one of the calculations that we need to make, because if it turns out that we need to size it up for it might end up becoming, we might need to dump faster than a solenoid can dump, and that would cause us to need to go to a pneumatic valve. But
do you have an idea of what instance you would have to, like, your dump rate would be a concern?
Because
I can't ever think of one where I've been like, oh no, this dump is too slow.
Yeah.
I mean, like solenoids usually don't have a super large CDA, right? So I think dump that ends up going from like order of minutes to order of like hour-ish, maybe, depending on how much you're loading on. Oh, I guess these are gonna be pretty low fill rate, or like fill anyways. But then I think for a solenoid, then you have to worry about all the like material compatibility with old elastomers inside, where if you run pneumatics, it might be slightly less of an issue.
Yeah, because I know, at least in my experience, I was doing propulsion tests over the summer, and I was working with hypergalls, and so that was kind of a much bigger issue for me. So material compatibility, I've found, hasn't been too much of an issue in a lot of the elastomers that are used in sealing for a lot of these valves. It is for a few.
Compared to hypergalls, this is going to be easy.
Yeah.
No temperature measurements on here, it looks like.
But I haven't not included thermocouples on this PNID. There are plans. It's kind of the main places that we're looking to measure temperature. I'm not sure, because we haven't really thought that it would be that important to have temperatures in the feed system itself. So that's mostly going to be measuring the temperature of the nozzle and of like different points along the nozzle. Is primarily we're going to be looking to take temperature measurements.
I mean, if I'm a student in this club and like president comes to me and says you get one, like president of the club comes to me and says you get one temperature sensor to put on the entire thing, I wouldn't put it on the nozzle. I would put it in the nitrous tank, I think. Like you're going to have a super strong correlation between your oxidizer density and pressure with temperature, because you're like, if you're deciding to use a self-press system, like you need to be able to tell what your temperature is to know what your pressure is. Well, I guess you have the pressure measurement, and then you can like back out temperature and then back out density. But like, I would rather just take the temperature in nitrous tank, I would say.
Mm-hmm.
Personally, I don't know if you have the juice, you can back some stuff out. Yeah, it might be good to have temperature, just something to look into. Not saying you 100% need it.
Yeah, and that is, especially with instrumentation, depending on, it shouldn't be too difficult to add more thermocouples. It's just a matter of if we have too many inputs than our DAC can handle. So that's the main trade for that, especially with thermocouples because they're fairly cheap and pretty easy to make. So thermocouples are kind of lesser concern just because they're theoretically easier to just add on at the end is the other reason.
If you're doing an inflow measurement, like it'll take more planning.
Yeah.
But yeah, either a thermocouple or an RTD.
Yeah.
Okay, I think I'm good to move to the next one.
And kicking it back to Adam.
Okay. So these are just planning ahead goals. Before I get into those, I wanted to touch on a few things. What was it? Oh, okay, yeah. Chris, on the ISP thing, you were totally right. I think it is 216 seconds. I had that in my code. I think I switched out the RPA value at some point and never updated it. But RPA was not assuming the combustion correctly. So thanks for catching that. What else? Oh yeah, all right. And then I wanted to talk a little bit about the self-press system. We were talking with Alex, a former CPSS member. I think that was his name.
Alex,
yeah. And one of the reasons why we decided to do a self-press, we originally had the nitrogen pressurization, but we switched because because we're regulated, we would have to regulate down so far. And 10 bar is way under the vaporization pressure of our nitrous. We didn't know if it was going to be two-phase flow through the feed system, and that was something he warned us against doing because, yeah, we weren't 100% sure of the phase because of such and
corrosion.
Yeah, and corrosion because of that. So,
sorry, who was this?
So he's I think he graduated in 2014. So he was one of the students who was helping develop the bi-prop the bi-prop that is currently in the lab. So he was one of the students who helped develop that.
Yeah.
And it was also in CPSS working on, I think, HM 3 or 4.
Are you sure it wasn't Alan?
Wasn't what? Sorry.
Alan?
No,
Yeah,
it was not Alan. It was one of Alan's friends in the club.
Okay.
And if it was Alan, I'd probably be open to it.
Yeah.
I mean, like,
I just wanted to give a little bit. I totally understand the concerns because nitrous is so hard to work with. But I just wanted to shed a little bit of background on why we did go away from that design. It was mainly because we weren't sure of the phase, and we couldn't get an exact answer.
I'm not entirely sure I understand why. I guess even with a reg system, you're going to have problems getting to 10 bar. Like, you're still going to self-pressurize anyway, so like regs help you go above press temp or press pressure, like self-press pressures, like saturation pressure. I think the problem is trying to go all the way down to 10 bar. Like, you need to have a pressure drop somewhere.
Yeah, I know, and we chose to do that across the injector. It seemed like it wasn't as big of an issue, but now going through this, it seems like we really have to worry about that stiffness.
He thought it was a pretty big issue. I think like creating such a large pressure drop inside the feed system creates corrosion in the pipes. I think he was concerned about that specifically.
Okay. Did you guys hear that?
Yeah, I'm just trying to like think about it a bit more. Yeah, it's just like super odd to me to have a 350% stiffness on an injector.
Yeah.
Instead of like 20%.
Yeah, if our combustion pressure was higher, then it would be as big of a problem. But.
Wait, but if you have a pressurant, then you can like, if you have a pressurant and you go above saturation pressure, then it's less likely to have two-phase flow. Am I tripping?
Yeah, well, I think the idea was
you're suppressing the transfer of gas.
Yeah, I think the idea was that with the regulation, since the main issue was that we're trying to supply less than, so we were trying to, since we were designing for 10 bar, we were trying to design the feed system such that we would supply less than that pressure. And so basically, if the idea was if we had to supply of that high of a pressure anyways, it would reduce complexities to simply get rid of those pipes, to get rid of the pressurizing the nitrous system and just have it self-press and have all of the pressure drop across the injector.
Yeah, I don't think you're going to have the entire pressure drop across the injector for one.
Okay.
Because you're going to have a lot of flow losses if you're using, especially if you're using 1/4 inch tubes. Like you'll end up taking quite a bit of flow losses through those, I would imagine, and then your injector is now incorrectly sized, and you're going to, I guess it's like not as bad. You'll shift lower in MR, and so you'll like burn colder. You'll just like take a huge ISP hit.
Makes sense. Okay. All right. Yeah. I think we gotta look more into it, and really, because.
Yeah, there's just a lot to think about, I think.
Well, we definitely hear what your guys' concerns are with that pressure drop over the injector. He didn't seem to be very worried about that pressure drop over the injector, right? Yeah, I don't know.
Yeah, because that is
I'm not
kind
saying
of,
he's all knowing, but it was just like the advice we got, so that's what we went with. But
yeah, just keep going.
all right, yeah. And then these goals are pretty self-explanatory. We got a lot to work on, obviously. Yeah, create testing procedures after we decide on these actual components and how they mate with each other and everything. Yeah, I mean, do you guys have any last questions? I don't want to take any more time just talking about random stuff.
Yeah, well, I think Miles just the delivery date.
Oh, what's the system delivery date? I mean, so our CDR is supposed to be at the end of this quarter, and then we want to manufacture and fire all during spring quarter, which is a tight timeline. I know, but.
That is very aggressive.
That is very tight. I would definitely start procuring material before that.
Well, yeah, definitely. We're going to start ordering it soon, actually.
As soon there's issues on the money side of being able to order things, but as soon as our money is cleared, we will start ordering things.
Yeah.
Don't listen to that business guy over there. Just buy it and ask for forgiveness.
Yeah. Sounds good. Yeah, and we're gonna, like, as we're working towards CDR, we're gonna be practicing a lot in the shop this quarter is the goal. Is to, so when we actually get in there to make these things, we know what we're doing. And we're not just banging our heads on machines.
Yeah.
Cool. Well, thank you guys. I know that was long. Thank you everyone else. Thank you to the prop team as well. We're probably going to take a break in between. I don't know.
Yeah, I think we could take so we're going to take a 10-minute break. So, but after this, there's going to be ground support going over the test stand. This should hopefully be it's much quicker. So we'll take a quick 10-minute break while we get that going on, and it looks like we'll start up at around 11:50 for the test stand design, because that's the other half of this, is that we are trying to make a new test stand that we can use kind of for our further liquid engines.
All right, I've got to head out. Just a heads up. Who can I ping to get some slides?
Okay, I think we're gonna start back up in a minute here. Sorry, we're a little late. There was some conversations going on in the background.
All good. Just heads up. I'm heading out. Good luck.
You're heading out right now?
Yeah, I've got to go to work.
Good. Thanks for coming.
My pleasure. If I'm gonna ping Tanuj to have him send me the slides, and then I can take a scroll through and offer feedback if you guys want it.
Yeah, that'd be great.
Or you guys can just tell me to shut off, which is also acceptable.
Matthew's saying that I think both of the sets of slides should be in the chat already. So
Dude, I'm too stupid to figure out how to get to the chat. I swear. It literally says chat and channel meetings is only available to team members, which if you graduated from Cal Poly more than like 6 months ago or whatever, you get banned.
I see. Okay.
So I'll email, or I'll have Tanuj email it to me.
Yeah, we'll figure that out.
Awesome. Thanks, y'all. Looking forward to making some fire.
All right, so I'll start. My name is Johan. I am the ground support lead, and
My name's Ryan. I'm the test stand lead, kind of, technically.
we're going to be talking about the current progress on the bi-prop test stand. So our goal is to design a test stand that's able to withstand, to support our liquid bi-prop engine, obviously. And so we decided we wanted to build this test stand not just for this specific engine, but for future bi-prop engines up to about 600 pounds, which is the largest we think we can realistically get away with at the school before they really start not wanting us to do stuff. So we've designed this stand to withstand up to about 600 pounds with a factor of safety of at least 2. We are designing it to be able to be trailer mounted, so we can take it to the desert or to other facilities like Pastoralis, which has offered to allow us to use their space as their spaceport. We also need to be delivering the force data from thrust and at least the axial direction. We've been talking about seeing if there's adding off-axis force measurements as well, but at least our main priority is the main thrust measurement. We also want to be delivering pressure data from the feed system and run tanks, and potentially as well from the chamber of the engine. We also want to be delivering temperature data as well, so we can give the props teams all the data they might need to verify their calculations and see how well our engine is, how well it was built. So first we're going to be talking about the materials of our test stand, and I'm going to hand it over to Will, who's going to talk about that.
Yeah, I'm Will. I did a lot of the structures with Ryan. For the structural materials, the 2 biggest materials we practically considered are steel and aluminum. And you can see a trade study matrix we did pretty early here. The matrix has 60-63, but we played around with switching around 60-61, which about doubles the strength of aluminum and doubles the price as well. Yeah, the grades here relative to steel, so steel is all 1, and then the grades for aluminum are either subjective for corrosion resistance and reconfigurability, or just a percentage of the steel value. And the reconfigurability rationale there is not that the tubes are more reconfigurable, but for aluminum you can get T-slot extrusions, which would let us build a test stand, and then if we want to upgrade it to say 1,200 pound force capacity in the future, we can just add more beams and take out the brackets and reconfigure it like that. And what we ended up deciding is that we wanted to go with T-slot aluminum because for one, it's strong enough. We did some preliminary FEA and found that we can get it within reasonable strength, so we didn't need to go to steel. And it's a lot more corrosion resistant than steel, so we didn't have to deal with like meticulously painting every part, because this is probably going to end up being stored outside. And for our CAD, we did 80, 20, 40 millimeter T-slot. That was just mainly for design purposes. And we're probably going to end up reaching out to a few different companies and try and get that donated, and we might have to go back and revise our CAD, depending on which T-slot vendor is willing to donate us, if any.
And that 40 millimeters is really close to 1.5 inches, so we could do a fairly easy switch over if we got supply from an American company that's using that sort of extrusion rather than the 40 millimeter.
Yeah, it should be pretty universal, so we have some flexibility there for multiple different vendors.
Okay. I'm going to go into the initial design that we actually came up with. So we selected to do a vertical design, a vertical test stand, and that was both looking at heritage at existing test stands from other schools and the test stand that we have here at the college already. And that was also partly due to a conversation with Dr. DeTuris, in which she mentioned to me that with a vertical test stand, we don't have to worry nearly as much about cooling of our propellants at any point through any of the testing or firing. We should have all of it flow out regardless of whether it's has any failures or any issues like that. We won't have an explosion waiting to happen just because of the orientation. So we chose to do 4 supports rather than 2. The test stand in the prop slab only has 2 vertical support beams, but we selected for 4, which gives us a little bit more support and off-axis forces. And let's say we take the stand into the future and we have bigger rocket engines on them, we might we may end up with some weirder off-axis forces, let's say, or overall we have a lot of thrust. We want to be able to control that sufficiently. The dimensions of the structure are about 6 foot tall, 2.5 foot wide, and 1 foot deep. And the main construction elements will just be like the brackets that are shown on the bottom there. We have like the normal 90-degree bracket that can go on the inside of a corner, the L-shaped bracket that can go on the outside, and that's going to depend on where in the structure we're looking at and what we need for that part of the structure. Like, for example, the very top of the stand, if we just used like L brackets or even those corner brackets, then the stand is only held together at that. Those beams are only held on by the friction of, let's say, like a T-nut being squeezed into the extrusion. So in those places we could do like through holes all the way through the aluminum. Then we have to look at more of like the shear of the aluminum and being able to support that load. But we should have, I think that would probably be stronger than relying on the friction purely. But everywhere else in the stand, it shouldn't be an issue to, I think, use like T-nuts and those like L brackets and corner braces and whatever else to hold the actual structure together. That gray plating on the back, that is a blast plate that we have the feed system on the back side of, and I'm going to go into that in a couple slides. We'll talk about the integration of the feed system into the stand, but the idea there is whatever happens with the bi-prop itself, if we have any major issues or something is catastrophic, hopefully the blast plate will keep our supply lines relatively separate from that whatever issues we're having, and we won't have anything, we won't cause any explosions is the idea. Also, this configuration and the feed system on the backside, all of it will be integrated together, including all of the electronics and the sensors and whatever else we have. So that if, let's say, we do end up going to Paso at some point, or we take this and mount it on a trailer, all of it can be pretty modular and just move as one unit and from place to place, and hopefully with minimal side pieces that need to come along with it. But that's going to vary based on our feed system design and also our data acquisition and our electronics design. But if we needed to, we should be able to have all of that be integrated just on the stand itself. Okay, I'm going to talk about some mechanical interfaces. Oh yeah.
Sorry if I'm misunderstanding. So what's your footprint on this?
The area footprint.
Yeah.
So it's those side pieces, the two the legs on the bottom. Those are 2 feet. So it's 5 feet wide, and then 3 feet. Sorry, 2.25 foot in the other dimension. So.
And your how tall? 6 feet.
Yeah. Which, I mean, we can, and that's all variable. This is kind of just the preliminary design. I felt would give us good access to all the components that we're working on, would allow for us to add bigger engines, hopefully would give us enough space for looking at and analyzing our plume of our rocket, so we can see if that's fully developed, and that would be the same with larger engines. And this is still in a size range that could be used in the props lab and possibly mounted on a trailer.
So a couple of considerations about the space. 6 feet high means that at some point to get something hooked up on you, you're gonna have to get up onto a ladder. So just think about that, right? You're gonna have to do a lot of vertical lifting to get something set up like this. In terms of trailer transport, think about how much of this you would have to break down, because I don't know if you want to hook the entire thing onto a trailer, right? So just consider what you would have to break down on it. Yeah, just because I think for me, sticking the entire thing in a trailer, especially with your data acquisition electronics, you're going to want to break stuff down anyway, right? You're not going to want to leave your load cell installed full time outdoors.
Right. Yeah, and okay, we'll definitely look into that, because I think one of our initial thoughts was to have this trailer just the stand be mounted to a trailer initially, and just have it meant for that purpose, and we would just do all of our testing on a trailer. But it seems as though that's not going to be the plan moving forward. The issues with access to a trailer, and also it seems like it'd be better to have it ground mounted and then just transportable. So.
And you're storing this in the prop lab?
That's where we would hopefully be doing our testing, at least as of this year. Moving forward, I'm not certain if it would stay there or if we would have to move it somewhere else. But
I know Cody does a bunch of storage in both the bays of the prop lab, right? So he unfortunately is going to win that argument every time. So it may be worthwhile kind of talking to Cody, figuring that out, and considering, hey, if I have to turn this into something that can break down pretty easily, how do I best do that?
Right.
Because I remember when we were doing testing for HM7 Heavy, we would effectively get in there Friday morning, and we would have to build scaffolding so we could access the top of the test stand to eventually do a lift to the full stack in. Terrible times. In retrospect, not a good idea. So just think about, because you are eventually going to have to break this and rebuild it somewhere on a field site, so you're going to be very limited on tooling you have. You have to fight to find flat ground in the first place. So just have those considerations.
Okay. Yeah, and we could possibly minimize the design a little bit. This was, I guess, the initial goal for us right now was to design a stand that could handle the loads that we're looking at, and take into consideration all of the rest of the feed system and integration with the prop side of things. But I think definitely we need to fine tune our design, and I need to talk to Cody for sure and make sure that we're on the same page as far as that's concerned. Okay, so then with mechanical interfaces, firstly I'll talk about how the load cell is mounted, because I didn't have an exact picture of that, but that the plate on the top that you can see on the very top of the stand, there is plate, there's in between there is a 1 foot piece of aluminum extrusion, and on the bottom there's another plate, and there's also 2 support pieces of extrusion on the edges of that. So the idea there is that we have a through hole going through the top plate, through the aluminum extrusion, and then through the bottom plate, and we have that bolt has a nut on it to compress those plates together, and the plates will also be bolted through the extrusion all around. and that'll go into the load cell. That should allow the distribution of the force that should allow for the force to be distributed along that whole surface of the plate, rather than trying to like get it just into one extrusion piece or something like that. So that and what we've seen in the FEA, which I'll talk about in a little bit, is that it actually does distribute that load out pretty well, out to the beams running along the top of the stand. That's how that interface works. And then on this slide, so the stand needs to allow for a small bit of vertical motion in the oh yeah, sorry, wrong thing. The stand needs to allow for a small bit of vertical motion in the actual rocket engine, because the load cell works on the principle of the change in the, I believe it's the resistance of the metal material in the load cell based on its like contraction. So we need to allow for a little bit of motion in the vertical direction, but it shouldn't be a lot of motion. But the way that we're going to account for that right now, at least, is we can get these the extrusion pieces with threaded ends, or we can tap them ourselves, and then we can just put in T-slot bolts that will slide up and down in the T-slot of the extrusion and be mounted into that horizontal rail that holds our test stand, or sorry, our rocket engine. So there should be, I mean, there's concerns about binding, and that's something that I'm thinking about, but I think for the low end rocket, for this just 25 pounds, we shouldn't have issues with binding in those joints, and that should allow for enough vertical motion to give us an accurate or relatively accurate reading on our actual thrust generation. In the future, with larger engines and with possibly more forces distributed in more interesting ways, we might need to switch to like a linear rail type system, so something that will mount onto the side of those extrusion pieces and then be able to roll linearly without binding on either side. And this, just to give a idea, is that vertical beam, I'm sorry, horizontal beam with the engine mounted to it. That's what we're looking at, the corner of that beam. And then as far as the actual engine itself, that bolt that comes down from the load cell will go through this middle extrusion piece, and we'll have two plates very similar to the top of the stand. And then we have either bolts or some sort of rod that will go through these two plates and then into the topmost plate of the injector. And that's going to be the main mechanical interface between the rocket engine and the test stand itself. And that, again, in theory, should distribute the load that's generated by the engine into the hole of that plate and then straight into the load cell, which is above it. And this should give us room to input the feed system and whatever, like the spark plug or whatever else we need, transducers of any sort, to take measurements on what we're looking at. Let's see. Okay, so we did some FEA on this design. It's minimized. There's elements taken out that don't actually add to the structural integrity of the stand. But what we did is generated a pretty fine mesh in SolidWorks and distributed the force along a 1 by 1 inch area under the top plate, which is where the force is going to be distributed through the bolt itself. And we applied 600 pound force to that surface. And this displacement graph that you see, the red, that's 500 times scale, and the maximum displacement was, on the order of 0.0 something millimeters, in that range, and that's without the horizontal beam that's actually going to have the rocket engine on it, that's going to support it. And we also saw the highest stress is concentrated on the very outside of those of the plate on the top surface, and then also in the middle extrusion piece underneath the plate. But these areas shouldn't be, especially that middle extrusion piece. It's not entirely concerning that that's going to have a high load, because it's going to be sandwiched between these two steel plates that should handle the load without any issue. And then on the outer sides, the load wasn't extremely high, and we'll talk about the factor safety right here. So the minimum factor safety we saw on any mesh elements was 2.5, which is above our goal, meaning this design can handle the 600-pound force that we were looking to achieve. And that minimum factor safety was seen on that picture up in the top right, that hole that's drilled through the center extrusion piece where the bolts is distributing the load from the rocket engine itself. And that's some mesh elements in that area had minimum factor of safety of 2.5, but almost everywhere else on the stand, the factor safety is greater than 10. So this is, we're very conservative. This should be able to support the loads that we're looking at least based on this analysis. And the elements that are even close to what our requirements are not areas of major concern, since the deformation of that aluminum isn't going to change the structural integrity of the stand itself.
So for the feed systems, our current plan is to have obviously the tanks for each of the propellants. We're gonna have run tanks so we can fill them up, and then for each run, those will be emptied as the run goes on. We'll have all the tanks are planned to be secured to the frame behind the blast shield, the blast plate, and all the plumbing to be routed up through and then down into the engine. So we're coordinating with propulsions. We're currently planning on using 1/4-inch stainless steel feed system lines. That's subject to change, but that's looking like the most likely solution for what we're going to use. We have a current estimate of around 45 to 51 bar for the pressures that we're going to need to withstand, and that's from what Props has told us about the nitrous. And then for all the routing, there's a lot of the stuff Matthew covered, but a lot of pressure regulators and hoses to the engine. We have burst discs for extra protection, and then we'll have all sorts of pressure sensors all around, monitoring different pressures in the nitrous and ethanol lines. The PID showed at least 9, but that's still subject to change. And again, the tube size and valve selection is still a bit up in the air because it's based on what we can get, final numbers for mass flow needed and the final pressures from Props. But once we know that, we can start actually getting all the parts that we need.
So you're adding burst discs and relief valves? It was to add 2 layers of safety in case for some reason the relief valves don't work. One of the main things is the department is really, really on edge with us building the engine. And so we want to add just like ultra redundant safety features, at least to show them for now that, look, we're trying to make this as safe as possible. I would push back against how to use burst discs just in general, because as soon as they burst, right, you have to make another one,
right,
which is slow and painful.
Yeah, I mean, the idea would be to have the burst disc set to a higher pressure than the safety, so it would only be used in an absolute emergency, like worst case emergency. So that would be the idea, is that the burst disc should be, even in an off-nominal case, wouldn't be used in any, like that would be if the pressure is rising much more rapidly than we were expecting, and then the safety valve can get rid of like the relief, is unsuccessful. Yeah, either if they're really
It's meant as the absolute last resort. They're not intended to be used for standard just dumps. But again, still subject to change as we refine and understand what we need for the feed system as we go on. So you've already seen the PNID. Matthew talked about it to death. But what we have here, and Ryan's going to talk a little bit, is kind of an example of how we would mount the feed system to the actual test stand.
Sure. Okay. Yeah. So this is behind the blast plate on the test stand on the backside, and this, yeah, it's just meant to be more of a visualization of what is possible for us to how we would route the feed system. These valves and the tanks are not, you know, what we would actually be using because we haven't spec'd those out yet. But this is more just to give an idea of what we could use and what we could do. So the idea is we mount the tanks and have everything in some way anchored to the extrusion itself, or like through the plate if it's light enough, and have the routing of the piping such that we can, let's say, use the nitrogen tank to pressurize the ethanol, which we can fill from the side, and then we have the valves. Here, let's get another view. We have those pneumatic valves controlled by either shop air, or if we're out at a test site, maybe another tank that we bring along, and this is routed up and over and dropped down into the rocket engine and fed around, hopefully in a more elegant way in the future, into the rocket engine.
Yeah, definitely consider how you're going to chain those bottles down. Obviously, they need to be tied down. Is your test stand like secure to the ground in any way, shape, or form?
Yeah. This is looking at the test stand that's in the props lab right now. There's the concrete bolts, and then yeah. They like, there's, I think right now on the stand in there they have just chains wrapped around certain components of the structure, and then tied to those concrete bolts. But that's something I need to look into if there's an easier or better way of doing that. But I was thinking we could mount something to any like area on those legs that we could use to hook our stand to the ground and make sure that it's stable and not going anywhere.
Yeah, I would strongly think about your tie-down points. In perhaps an uneducated way, I'm a little concerned about tying down your bottles directly to the test stand. I think they still need to be chained down, but I would almost rather have them separated from it. I wouldn't have those two things linked, because if one takes off, the entire thing's going to take off. Yeah, really think about your tie-down points on this.
Okay.
I have a big fear that the structure itself is going to be very flexible, especially if you're doing 600-pound force. That's when you start to have a lot of concerns.
Right. Okay. Yeah. Yeah, and that's a good point. And hopefully the feed system itself, when we have that a little bit more fleshed out specifically, and we have valves and like the actual run tanks and the supply tanks, will have a better idea of how that might look and how we might mount that together. But we can move those supply tanks somewhere else and just have a connection for them, and or maybe even like their own carriers of some sort that keep them separate.
So in terms of sensors, we're planning to take all of our data through LabVIEW, which is pretty standard in industry and standard in our own labs. So we're going to be using multiple different sensors to gather data. Main one, obviously, is the load cell. We're going to be using an S-beam load cell. We hope to get one from like Omega or Futech. But we also plan to have this load cell be swappable, so for larger loads. So the load cells that we want to use right now would have a max force of 100 pounds, but we would be able to swap them out for max 1,000 pounds or lower potentially, whatever we're able to get our hands on. Because as I was doing research for finding load cells, there's not a whole lot of places that have it in stock, still kind of reeling from the supply chain issues of COVID and all that. And so so our supplies are limited, our options are limited, and so we might just have to use what we can get our hands on, because there were lead times of anywhere between 4 and 10 weeks to get your hands on a load cell. which for the tight time schedule that we want to be able to be testing and firing our engine in spring, having a 10-week lead time on a load cell plus however long it actually ends up getting here is just not reasonable. So we're designing to be as flexible as we can with some of these parts because of availability issues. We'll have pressure transducers all throughout the system, like was shown in the PNID. There's at least 9 that are shown there, but there could be potentially more if we do monitor the chamber pressure of the engine directly, or if we remove other sensors. So I'd imagine, so as a final number, it would probably be anywhere between 5 and 11 pressure sensors, again, subject to change as we refine the design more. And then we're also planning on having thermocouples in a few different places. We are hoping to monitor potentially engine temperature, and then, as Chris mentioned, it'd probably be pertinent to monitor the temperature of the nitrous tank as well. So we want to have the capability of having at least a couple thermocouples provide data back to the users. So we're going to be using National Instruments DAC system. Which one we're going to use, again, is still a bit up in the air. There's one we have currently that's in the corpus of HAL that we might salvage, but depending on our needs, we may look into getting a newer DAC so we can have more data inputs. But for now, we're going to try and use the one we already have. But again, depending on supplies and time and money, we at least have something to work with. So we'll be having all the sensors input through the DAC and then outputting to a computer that we are in talks with Deturis about getting specifically for us that will be used in the prompt lab. And that will have LabVIEW running on it, where that will actually take all of our data and compile it to give to whoever wants to use it, probably props, I'd imagine. So we also want to make sure, again, talking about the modularity and availability issues, we want all the sensors to be able to be swapped out if necessary, because as part of availability, we also, since we are planning on having this test stand be capable of supporting up to 600-pound plus engines, the sensors and load cells that we use for the lower powered engines that we're building right now won't work for larger engines. So if we want to have this test stand last a long time and be able to be used for future projects, then having those be swapped out is ideal. So we'll probably come up with try and make connectors that can be easily swapped out with the load cells and sensors, but that's still to be determined. And depending on time constraints, we might just forego that for the time being, just so that we can actually run a test. Like I said, all of our data acquisition will be done through LabVIEW. And then safety. Again, because the department is quite concerned about just working with bi-prop engines, we wanted to focus on safety a lot, because we don't want anybody to get injured. We want to try and have as safe of a run as possible. And the more things we can do to the test stand to make the environment safer, the more likely we can hopefully do future tests and develop more engines and newer products. So we'll be having a blast plate, which is where all of our plumbing is to be mounted to protect the run tanks and all of that in case of a catastrophic failure from the engine itself. We're planning on having a flame diverter to try and get all the exhaust gases out. So if it's mounted in the props lab, we'll have the flame diverter pointing such that all that gets blown out of the open doors and then into the air, so that if there are potential issues, they don't pool up inside the lab itself. Then relief valves and burst discs we talked about already. In case of overpressurization, we can dump the system very quickly. But if for some reason those relief valves don't work, we'll have those burst discs as an absolute last resort. And then we'll be drafting up rules, procedures, regulations, and have safety data sheets on hand for nitrous, ethanol, and other potential propellants that we might use. And we'll have very clearly defined rules and call outs for different stages in the testing process. And then as we develop the firing mechanism, we'll make sure that there are redundancies there such that you need like 2 keys to turn it on before you can fire. So we want to make sure that nothing bad happens on the test stand part. We don't want it flying away. We don't want people getting injured. So safety is extremely important in that regard. And then as we go on, we'll be refining the design, finalizing feed system parameters with props, developing a firing mechanism with them as well, and then coding up our LabVIEW interfaces and acquiring all our materials.
Yeah, and kind of to go on the safety aspect of that as well, part of that is going into the DAC side, adding autonomous capability of being able to monitor, control, and fire all remotely from and fill burst reactors to avoid any, so that there is never any technician working on the test stand while there are any propellants on stand.
Will the actual arming and firing, will that be done with like the lunchbox thing you've been making, or will it be done with the actual?
No, it'll be the lunchbox thing was for just testing small solids.
So everything, like all the firing and arming, that's the prop lab's own infrastructure.
No,
we'll be building our own.
Like the idea is you can have outputs through LabVIEW to control things like relays and to control valves. So that way we don't have to develop all of these like mechanical switches. We can run everything through LabVIEw, and also we don't have to. When we're moving the stand, we don't have to worry about taking the control panel with us.
So everything's in.
That will be the idea.
I would be cautious with that, just because the ability to like make a misclick to accidentally start a fire is always obviously bad, which is part of the benefit of why those two systems are separated.
Yeah, so
you have your mechanical limitation on it.
So what I was thinking was that we'd have, we'd have like manual controls again, just in case, and then
there's also ways of running buttons and mechanical interfaces through LabVIEw as well. So it's not a click of the button; you can move that button into the real world.
Okay, so you have like a physical switch, which then pumps in the LabVIEw, which then starts.
Although I'm personally a bit skeptical with LabVIEW because of the amount of times that we've had issues with it when running our actual labs. But again, redundancy, just so that we don't have a single point of failure. And then if something goes wrong, like LabVIEW crashes, then in the middle of a firing, we can still abort the test if needed.
I would definitely look at some of the documentation we have that Matthew and I made for how our freshman year, because it'll help get through like what their control flow was in terms of switching between the lunchbox and then what they actually were controlling like remotely and like virtually, because they had a pretty good system of having like critical functions being controlled through the lunchbox, but then running those into the I/O module we had, and then also having outputs that were control signals running out of that.
That's the end of the presentation. So if anyone has any questions for us or anything.
Other comments,
thoughts,
concerns?
Great job.
Thanks.
Thank you.
Looks great.